Good morning, everyone. It is our pleasure to extend a warm welcome to all the distinguished professors and participants attending the inaugural session of the GIAN course on Advances in Solar Collector Technologies. We are honored to have with us today Professor Christophe Ménézo from France and the head of Center for Education Technology and head of School of Energy Science and Engineering, and Professor Pankaj Kalita, the host faculty of the course. We extend our heartfelt welcome to them. To mark the auspicious beginning of this event, we now invite the dignitaries to participate in the traditional lighting of the lamp. Sir, please. Thank you, professors. May I now request all the dignitaries to please sit on the dais? Sir. Please. At this moment, I would like to request the head of Center for Education Technology to felicitate Professor Christophe with a Fulam Gamusa. No. Thank you, sir. Now I invite Dr. Pankaj Kalita to provide a brief overview of the course. Sir, please.
A very good morning to one and all present in this hall. It is with great pleasure I extend a warm welcome to all the participants and guests to this global initiative of academic network program on advances in solar collector technologies at IIT Guwahati. At the outset, I would like to express my sincere gratitude to our esteemed dignitaries, Professor Christophe Ménézo. He is a professor at the University of Savoie Mont-Blanc in France, and he is also director of Solar Energy Research Federation in France. Professor T.V. Bharat, he is the head of Center for Education Technology at IIT Guwahati. Professor V.V. Gore, he is the head of the School of Energy Science and Engineering at our institute. This GIAN course was conceptualized in collaboration with Professor Christophe in 2023. Initially, the event was planned in 2024, but this could not happen because of a lot of administrative changes in the GIAN program. Finally, we make it happen today. So it's a big day for us. So about the GIAN course, it's a 5-day program. It's a very, very comprehensive program. And mostly we prefer in-person in this event, even though we have about 15 students, they are attending online. And this course aims to provide comprehensive knowledge on solar collector technologies, covering both fundamental concepts and advanced applications. So as you know, the mandate of Government of India, the amount of solar we're expecting by 2030. So it is close to 500 gigawatt. So we need the contribution from all the fields of renewable energy, primarily in renewable energy sectors. Also, there are a lot of potentials to capture solar energy potential in different part of the country. The key areas to be focused in this course are recent advancement in solar collector technologies, such as building integrated photovoltaic systems. We call it as BIPVs in shorts. Then solar PVT systems like photovoltaic thermal collector systems, which are very, very advanced systems. Then concentrated photovoltaic thermal collectors. And also will include optimization strategies and system integration for sustainable development, and challenges and future prospect of solar collector technologies. The course is designed for researcher, entrepreneurs, and industry professionals at medium to senior level who seeks to enhance their expertise in solar energy technologies. So finally, we have planned to provide the state-of-the-art knowledge in this context of solar thermal systems. In this entire course, about 60% of the lectures will be delivered by the foreign experts, because the course is designed in such a way that, or as per the mandate of GIAN, so 60% has to be provided by the foreign expert and 40% by local expert. It's me. And on the top of it, we can invite some high-profile people. So in our course, we have invited one Marie Curie fellow from Glasgow University. He will be delivering one and a half hour talk on solar collector. He is exclusively working on solar PVT collectors. And daily sessions will start at around 9:30 every day, and it concludes at 5 o'clock. And attendance is mandatory for all the sessions, because as per the GIAN mandate, we need to provide the list of attendees who have attended the entire lectures. And on the final day, that is on 7th of March 2025, there will be one exam. It's a 1-hour exam. Those who are interested to gain 1 credit, then they can write for the exam and they can claim for credits. So you'll get a credit card from IIT Guwahati. So sometimes nowadays, as you know, it's online programs now, and then university prefers online courses from MOOCs and other online platform. So you can claim that you have already earned 1 credit. So that is very, very essential for students, those who are doing engineering and master degree in different engineering colleges. And it's a 1 credit, you must remember. So in conclusions, once again, I extend my warmest welcome to all the participants. I hope this course provides to the enriching, memorable, and intellectually stimulating. experience for each one of you. I wish you a productive and enjoyable stay at IIT Guwahati. Thank you so much.
Thank you, sir, for all the information. Now, I would like to request Professor T.V. Bharat to present an overview of the GIAN initiative that is coordinated by Center for Education Technology. Sir.
Thank you. Thank you. Professor Vaibhav Ghaud, Dr. Pankaj Kalita, and all the colleagues and fraternity of IIT Guwahati, on behalf of all of us, we extend warm welcome to Professor Christophe from France to this particular GIAN program, and also at the same time I would like to invite or welcome all of you, all the participants who are present today in physical mode as well as in virtual mode, to IIT Guwahati and particularly Center for Educational Technology CET. This GIAN is a global initiative for academic networks, is an initiative of Government of India which has started its phase 1 in 2014, and over the years, around 11 years, number of phases have happened. 3 phases already concluded, and number of programs have been conducted across India, and several experts from the globe, different parts of the globe, have traveled to India and then participated in the GIAN programs. GIAN 4, phase 4, which started around 2023, initiated in the 2023, and then we sought proposals from different fraternity of IIT Guwahati, had some kind of changes in the administration process, as Dr. Kalita has mentioned, and so therefore there is some delay that has happened, and finally from IIT Guwahati alone 20 proposals have been submitted, large number, and 13 are already on board, and we have already conducted 5 programs, and 2 more we will yet to hear. So that is the status. Around 15 we are going to conduct this phase 4 from IIT Guwahati, and in fact phase 5 is also going to open very shortly. So soon it will be up, GIAN 5 as well. And Center for Educational Technology, CET, is a interdisciplinary centers and 5 schools. And apart from this, we have extramural centers like CET, Center for Educational Technology. From NPTEL initial days, the CET has been formulated here in 2002 and taken up number of government initiated projects like NPTEL MOOC and defense programs, and GIAN is one of those priority areas where we've been conducting. So far in NPTEL itself, we have obtained 700 courses that have been developed here at IIT Guwahati itself, and we have number of labs, editing labs, studios, where we have recorded and edited all the courses which are up on the YouTube. And the GIAN courses, the advantage is that even this particular course, which is 1 week duration, can go into NPTEL, right? So we are looking forward to have this particular content slowly developed into NPTEL, which are available for all of us for free of cost. And number of registrations also taking place, and certificates are also awarded on this, right? And GIAN has a very, very important program, important initiative of Government of India, where foreign faculty gets to engage with the Indian researchers for about 1 week to 2 weeks time, and he will be fully available, unlike like a conference where your engagement is only limited to 1 hour, 2 hours, etc. But here you have an opportunity to engage with him, engage in discussions and clarify doubts and understand the global perspective of certain advances like advances in solar collector technologies. and that is very important, and that is advantageous, and you have a beautiful campus environment, and it's a particularly this particular period is very pleasant time to stay in IIT Guwahati, in fact in Guwahati. Coming to the course, although I am from civil engineering background, but I can connect these renewable energy sources. The climatic conditions are quite different, especially in Northeast India. You might be knowing that highest rainfall that is received around more than 2000 mm per annum is received from one of the places hardly 100 kilometers from here, Mysonram. Earlier it was Cherrapunji, now it's Mysonram in Meghalaya. So having said that, having several monsoons starting from very almost March to April, so when whole country will be steaming with heat, but Assam receives rainfall from mid-March to April, and it continues up to September, nearly 9 months of rainfall. So when we are having these solar energy panels, etc., so the challenges that we face, because the France conditions might be different, so those things can be discussed so that it will be a win-win situation. How to optimize the efficiency of solar panels here under these conditions would be one of the ideal thing that Dr. Pankaj has actually given a very meticulous planned syllabus or course outline. So I'm very sure this program will be very successful, and I encourage all the participants to engage not just in discussions and also beyond this particular GIAN course, develop networking and also start communicating and then work together. And I wish all the best, and I hope this will be a grand success. Thank you so much.
Thank you, sir, for your enlightening words. Now I request Professor V.V. Godser to provide a brief introduction of the School of Energy Science and Engineering to all the participants. Sir.
Distinguished guests on the dais, my faculty colleagues, participants and student members, good morning, and I welcome you all to this GIAN course on advances in solar collector technologies. As we know, we are gathered here to embark on this journey of learning and innovation in the field of solar energy engineering. And why it is so? Because it is a very important area in the renewable energy to harness this particular energy to produce heat and the power, right? So this course, as Dr. Kalita has already mentioned, the course is aiming at developing knowledge in this particular field of solar collector technology, as well as the advancement which is happening around the world in the form of like using nanofluids in the collectors, or maybe having the hybrid system for solar collector technologies. So all those aspects would be covered in this particular course, and I think it's a very right moment to have this particular course as well, because the world is transitioning towards this particular area of the sustainable energy, and in that solar energy is trying to play a very important role, as I mentioned, in the form of power and the heat generation. So with this, I guess this particular course will cover all aspects and the new designing, the the materials which would be useful in this particular collector technologies. And I also thank the expert from foreign, Professor Christophe, for joining us for this particular GIAN course, and through his knowledge as well as ideas and the research, we'll try to learn some new things which his country would be adopting in the field of solar collector technologies, as well as it will be a win-win situation, as Professor Bharat has already mentioned, for the country like India also to adopt such technologies. And this particular courses always helps in kind of bridging a gap between the technologies, as well as to have the partnership between the countries. So this is not mere a kind of a course which will help only to a participant, but as well as in the broader aspect, it helps to the institutions like IIT Guwahati, as well as the institute like in the France, as well as the industries involved in this particular technologies. And I also congratulate the Indian expert Professor Kalita for timely launching this particular course, and I hope this course will definitely benefits to the participant as well as the student members, those who are participating in this particular course. And at the outset, being the head of the school, I'm duty bound to brief you about the school and its activity as well. The school was earlier known as Center for Energy. So in 2022, we converted this into a School of Energy Science and Engineering. And then in 2022, we launched a BTech program in this particular school. And that was basically a reason to convert Center to a School of Energy Science and Engineering. And with the initial intake of only 20 students in the BTech, but we are successfully running this particular program since last 3 years. And another June, July, we'll be admitting the next batch of the student as well in this particular course. Apart from that, we have Master of Science by Research, a very unique course which is designed. And I'm very proud to say this everywhere that the Center for Energy was the initiator to start this Master of Science by Research in the institute. And after that, it has become a very successful program, and it has been adopted by many other centers as well in the IIT Guwahati. And apart from that, we also have a regular PhD programs where the intake is very good, and we have very good strength of the PhD students, as well as we also admit the IPDF students also in the school, and we have very good number of the IPDF students in the school as well. And apart from that, we are also doing very good in the form of like renewable energy research. If you can see our website, you will be happy to learn that the School of Energy Science and Engineering has done a very advanced level research in the field of renewable energy. And not only in the field of renewable energy, I would say in the area of the conventional energy also we are doing a bit of research that is in the field of coal gasification, because Professor Kalita or Dr. Kalita will also brief you, I think, sometimes in this course, the activities which he is doing in this particular school. Apart from that, we also have adjunct and associated faculties in this school, and those are also actively working in this area of renewable energy as well as the non-renewable energy resources. And apart from that, some of our staff members are also actively working in the area of renewable energies. They are running some kind of projects and the program which caters the needs of this northeastern region as well. And one of such particular center is nothing but Biogas Training Development Center we are running from the School of Energy Science and Engineering, and this particular center is sponsored by Ministry of New and Renewable Energy. And with this, maybe I will not extend too much, because I know you are eager to listen to the speakers rather than listening to us. So I will just cut short here, and I wish you all a very pleasant stay in IIT Guwahati. And my sincere request to all of you is like to actively participate in all these lectures, listen to the experts from India as well as foreign, their idea, their knowledge, their thought process in this particular field of advancement in the solar collector technologies. Thank you all.
Thank you, sir, for the informative talk. Now I request Professor Christophe to share his valuable words with us. Before that, I would like to present a brief bio about him. Professor Christophe Ménézo is the director of the LOCIE laboratory, UMR CNRS 5271 at University of Savoie, Mont-Blanc. He serves as the director of the National Solar Energy CNRS Research Federation, Solar Energy Federation FR 3344. He holds significant leadership roles in solar energy research, including deputy head of the Solar Academy Graduate School. His expertise include hybrid solar PVT collectors, energy management, adaptive facades, and sustainable building solutions. He is a recognized authority in the field with over 67 journal publications, 23 supervised PhDs, and a Scopus H index of 33. His notable accolades include the Best Solar Energy Researcher in France in 2017 and in the Chinese Academy of Sciences President's International Fellowship Initiative. So, with that, I welcome Sir to deliver his talk. Sir, yes.
Thank you very much. I didn't prepare a talk, but I will try. I'm very happy and certainly very proud to be there and to have been awarded by the GIAN program. As you will see, the topic is large and I have many things to do, to tell, and I hope to learn also to you. I know that most of you have already passed also in solar energy, so don't hesitate if you have some question. If you don't agree with me, I'm also ready to be challenged. And so the lecture for this week is quite heavy, so I will try to be interesting in order to avoid you to sleep during the afternoon, and to give you examples that could interest you. We will try to give you some tutorials also regarding different topics. The aim is to highlight some important point about solar technology, but there is so many. It's a very interesting field, and at each innovation there is a new challenge, because our aim is to improve the performance of such components and also the reliability, because sometimes there is some decrease of some performance that are not well understood. And so we try to give some knowledge on this, the reason of this decrease, and also how to treat this decrease. I'm thinking about, for example, at that time, a soiling effect, which is very important, but also a lot of different effects regarding PV central. I know that in India you are you have a high level of knowledge about hybrid solar PVT, because I regularly have to review some PhD. Started to work on the topics in 2005, and I know that in India they keep on have some research, very interesting research on this area, which is not fully defined and finished. There is so many improvements that could be done in this area, and also some other kind of needs when they are integrated in systems. So we'll try to give you some data about this, also some how to design such a system, and don't hesitate if you need afterwards more details or more information about the topics, because we couldn't go so deeply in each topic. So after, I'm ready to answer to you if you write me to give you more data on a specific area. Regarding the reliability, I don't know if I will have time this week, but some interesting developments also are considering the modeling and how to predict, of course, how to be able to predict the performance and the production of PV central. And I think you are all aware of the deep development of deep learning. And it is some very interesting tools, especially for the prediction, and so the management of the maintenance of such a central. At the last day, we will see how the factor could impact the performance, and we'll made a short introduction about startups that we have developed in the laboratory, working on it, how to be able to predict when it is necessary to clean, for example, a PV central. When there is a problem on big central, it's not so easy to identify where there is a panel which is not working anymore and things like this. So I hope I will have time to speak about that also, but there is many opportunities to make some research on these fields, and so much issue and challenge that I'm very happy to be there to share that with you. Thank you very much.
Thank you, sir. We are eagerly waiting for your lectures. With this, we conclude the inaugural session. All participants are requested to join lecture 1 after the tea break, and we look forward to see you all again. Thank you. And the tea break is for 10 minutes. Okay. Thank you all. Welcome you all again. So now we are proceeding for the next session, that is day one, lecture one. Before that, I would like to give a brief introduction about our host faculty, Dr. Pankaj Kalita. Dr. Pankaj Kalita is an associate professor in the School of Energy Science and Engineering, Indian Institute of Technology, Guwahati. His current areas of research include solar energy conversion, thermochemical and biochemical conversion, energy management, energy storage, and integration of renewable energy for remote electrification. He has published more than 100 articles in various peer-reviewed journals and conferences with a Scopus H index of 23. Also, he has successfully supervised almost 10 PhD students. He has also contributed many chapters in different book volumes. Further, he has edited 4 book volumes so far. He has successfully implemented several research projects funded by different government and private agencies in the fields of energy generation, energy management, energy modeling, solar power plant design, energy testing, etc. He is currently offering 2 MOOCs under SWAYAM NPTEL in solar energy engineering and technology and sustainable power generation systems. So with that, I am inviting Dr. Kalita to take the lecture 1, and over to you, sir. Thank you.
Thank you, Buki. So this lecture will continue for 2 hours, and then we'll have 1.5 hour, probably very close to 2 hours, what is called a tutorial. Okay, so let's see how fast we can go, and it's a very long presentation because, as you can see in the slide, content like solar geometry, fundamentals, design of solar thermal collectors are there. So mostly in these presentations we are going to address the very, very fundamental things required for designing a flat plate collector. Okay. So before we start our forward presentations on the topic what is mentioned in the title slide, so we need to know, like, why do we need energy? What is the demand? And then what is happening in a global perspective if we say the demand and then the kind of fuel we are burning for generating energy. Then the climate change and the adverse effect. Then the fundamentals of thermal collectors and its classification. Then propagation of solar radiation geometry, how radiation can be estimated. Then thermal energy storage, and then finally various applications of solar collectors. So now let us see the progress of energy use. If we see the evolution of power generation, it's long back, 200,000 BC, when control fire was invented. Okay, then slowly we move towards use of coal for heating and cooling applications or cooking applications. Then we have coal power plants. Then we can see first hydroelectric power plant was commercialized in about 1882s. And then if you go down, then about 1888, we can see the power generation from wind turbines, right? And then we have first geothermal district heating system in 1892. And then now what we are looking for is really a sustainable power generation system, okay? Because of many, many reasons, right? And also you can see how this demand is increasing globally. And if you see the entire requirement of energy, it actually mostly comes from is fossil-based fuels. Okay, so still we can say it is more than 65% energy is coming from fossil-based fuel, right? And also we talked about quality of life, like human development index. So this human development index is related to amount of power or energy you consume, right, in kilowatt hour. So that means when we talk about quality of life, that means we are actually consuming more fuel for increasing the comfort and quality of life, right? Then we will see what happens if this is the case. And this is the scenario for Indian context, and this is a very recent data. You can see the contribution from coal, gas, lignite and diesel it is about close to 60%, and then we'll have solar about 21.2%, then wind about 10.4, hydro is 10.2, and rest is very minimal, but contribution is there. Okay, but what my concern is like this part. Okay, so this is not real. So coal part and then fossil part. Okay, it contributes about 60%. Okay. Now we need energy production. That means we need to burn, because mostly energy is coming from fossil-based fuel, and that leads to actually global warming and greenhouse gas emission to the Earth atmosphere, right? And this is the share of carbon dioxide emission by different countries. As you can see here, China is taking the driver's seats, and then we are also not far behind, and then USA and other shares you can see here. Okay. Now this curve is known as killing curve, generated by Mauna Loa Observatory in Hawaii, in USA. Okay. So what information you will get here? This carbon dioxide concentration is increasing with years. So if you see about so 1750, it was so it's close to 280. Okay, so safe limit of carbon dioxide in the Earth atmosphere is 350 ppm. Right, so it was far below. It was very, very comfortable. Then when this industrial revolution starts, and you can see the rise in carbon dioxide level. So if you magnify this part, the latter part after 2000, you can see here this kind of pattern. Okay, it's very, very high, and it crosses 420. So this is a very recent data, and it was in 2 days back I have taken this data. It is about 426.71 ppm. So already we are in a very dangerous state. Okay, we need to take measure. What are the technologies we can use to reduce those carbon dioxide in the Earth atmosphere? So as you see, climate change, there are various reports on melting of glaciers, right? Then you can say a rise in global warming. Here you can see at the top of Earth what we have on the thermometer we put, and it shows about rise in temperature. Then rising sea level, unexpected floods, and then adverse climatic conditions, burning forest, and then drought, you cannot cultivate properly. So there are various indicators what you can say this climate change is really occurring, and it is very, very significant. We can see the visible changes, right? Now what is required for us is renewable energy systems. Of course we cannot remove fossil fuel in a day, but slowly you can actually replace these coal-based power plants or maybe other fossil-based power plants. So it may be solar PV, it may be solar thermal, it may be wind, it may be hydro, it may be biomass resources, or it may be some hybrid systems, it may be ocean, it may be OTEC, okay, it may be wave, or it may be geothermal, or it may be integration of renewable energy systems. So we need appropriate technology based on the resources available. Okay, so it's not something like always we need to build very big unit. In my opinion, we need to optimize it based on the requirement, and we need to have all the technologies in board for sustainability. Now, if you see solar thermal global scenario, you can see in the net, and this is the source from where I have taken this data. So it normally tells about area, the amount of area we use for collection of solar energy. Okay, so here in China you can see how much area they have used for collection of solar thermal, and then you can see other, and then in India we are also not bad. It's about 15 lakhs, okay, 15 lakhs square meter area is covered by solar thermal, okay, actually to the 2022 report. But here the second plot, what you can see, it's a solar thermal installed capacity. It is something like kilowatt thermal per 1000 inhabitants. So since our population is very high, so our name is not there in this list. Okay, so it's very minimal because of the population, right? And of course, France position is not there in the same plot. So it's quite interesting, right? So you can say like how much thermal energy you have harvested per 1000 inhabitant. Okay. And also you must know one thing: if you devise a flat plate collector of area 2 square meter, so you can actually reduce 195 kilogram of carbon dioxide per year. That's quite interesting. Now we'll discuss something about the different modes of exploiting solar energy. Already you are aware, it is something like a direct conversion from solar radiation to electricity, this solar PV. Then we can go for some kind of panels, solar hot water systems, and we can generate moderate heat. Okay, and that heat can be used for thermal applications. Also, we can use for electricity production if we have some kind of device which concentrate the solar radiations, and this is also thermal route. Okay, you just intensify the solar radiations, then you generate heat, then you exchange that heat with that working fluid, and then you use conventional Rankine cycle and then produce electricity, right? So it looks something like this. Mostly this solar flat plate collectors we install over the rooftops, right? And it depends the kind of flat plate collectors we use. It may be flat plate collector, it may be evacuated tube collector, it may be heat pipe collectors. So these are different generations of flat plate collectors. Earlier we had only flat plate collectors. Then what was the concern? We need to enhance the efficiency. So how to enhance the efficiency? So you come to know the different parameters which influences the performance of solar flat plate collector. Okay. So can we increase the transmissivity of the glass? Can we use some kind of selective coatings which increases the absorptivity of solar radiations and reduces the emissivity of the radiations? Can we use some other mechanisms which actually enhances the efficiency? Something like when we use to bond, like pressure bonding is done when we have flat plate collectors and then tubes, then we need to attach somewhere. We need to apply some kind of material there to fix it. So what could be the thermal resistances offered by this foreign material? So can we remove it? So these are the challenges, and that's how like evacuated tube collectors. So what they did, they actually try to reduce the convective heat transfer so that they can maximize the energy conversion, right? So that's how development is there. But one thing it is clear, this has to be installed over the roof space. Okay, and here in case of solar PV, that can be over the roof space or maybe in the ground. Okay, so you can have solar modules. You need to convert this direct current to the alternating current. Then you transmit to your what is called transmitter, and then it transmits power by using other electrical components. Okay. Nowadays we have net meter system. So the energy you generate, you can actually know if you are not utilizing, you can give it to the grid, and when you require, you can take it from the grid. A net meter will count the amount of energy you have delivered and amount of energy you have consumed, and that way you need to pay the bills, or maybe you can gain the money in terms of selling the electricity. Okay. Now we'll spend more time on solar thermal collectors. So what is solar thermal collector? It's a device, right, to collect solar energy and transform it into thermal energy by using heat transfer fluid like water, air, ethylene glycol, or maybe other fluid. Can you tell me at what condition we need to use ethylene glycol? Can someone tell me? And what condition we go for water? You can see water everywhere. Suppose if we suggest this technology in Ladakh or maybe Siachen, this will not work, right? It will freeze. So we need a fluid which will never freeze, right? So that's how glycol is used. So freezing point, you can find out now what is the freezing point of glycol, right? Now thermal energy systems provide thermal energy for various processes. For cold climates, it is very, very effective, because in our place we never experience for heating. We need actually cooling in summer, not heating. Hardly we use heaters, except those who are staying in high altitude areas, like it is more than maybe 500 meter from the sea level. Okay, but mostly we are below the 500 level, so we don't need that much of heating things, but we need cooling. Okay, that's how we are stressing more on vapor absorption refrigeration system. Can we have a low cost vapor absorption refrigeration system? Can we have a solar assisted dehumidifier? These are a requirement for us. Even in high temperature heating applications, significant amount of fuel can be saved by using solar collector preheating. So these are primary applications across the globe. We can also characterize or classify the flat plate collectors as per this. So it may be concentrating collector or maybe non-concentrating collectors. If it is a flat plate collectors, you are not concentrating the beams, right? So amount of solar radiation falling on your collector and the amount of radiations you are receiving is same. So area is same. So that means your concentration ratio is 1. So if you are increasing the concentration ratio, that means the area you are increasing, area of reflection. So for example, if I say concentrator, solar radiation comes and parabolic concentration, it strikes on the concentrator, then it goes back to the receiver. Okay, so if you now compare to the area of the concentrator, area of the absorber, both are different, right? So it is like area of the concentrator to the area of the absorber, so it is more than 1, right? So that's how we can say that how intense heat will be if we increase the concentration of the system, right? So that's how we can classify concentrating and non-concentrating collectors. Okay, and there are many classes on non-concentrating. It may be flat plate collectors, unglazed collectors. Sometimes we never apply glasses. Maybe in plastics, we can use plastics. Solar radiation can transmit, but what will be the transmissivity of the plastic or polythene? What I mean. Or glazing, we have glasses. So what could be the transmissivity? So transmissivity is something like, in technical terms we call it as extinction coefficient. What could be the extinction coefficient of the glass? Then solar air heater, it may be glazed or it may be unglazed. Then evacuated tube collectors, again we can classify these evacuated tube collectors in different categories. It may be water in glass, it may be U-type, or it may be heat pipe. Okay, and under concentrating, it may be flat concentrator, and we can have flat plate, but we can give some kind of additional mirrors to reflect the radiation to that collector, so that we can increase the concentration ratio of the system, so that we can make it workable at higher temperature than normal flat plate collector. Then compound parabolic collector, then parabolic trough collectors, we have linear Fresnel, then heliostat, then parabolic disc collectors. Okay, so these are building integrated solar thermal systems, what is called BIST. And sometimes you can see some hybrid systems like concentrating flat concentrator, or it may be compound parabolic collectors. So you can name it, but no basic concept is same. You want solar radiation from the sun and you need to convert it to thermal energy. Okay, sometimes we can use this technology for electrical energy production as well, but its conversion efficiency is low. Okay, if we work at flat plate collector, suppose you have a flat plate collector, but your demand is to generate electricity, it is also possible, because you have organic fluids which actually which boils at low temperature, and you can generate some vapor, and that is okay for generating some kind of power. But the efficiency of that kind of collector is very, very less. It is about 5 to 7%. Okay, but in case of parabolic trough, or maybe linear Fresnel, or maybe heliostat, so you can go up to a temperature of 600 to 700 degrees Celsius. Okay, so it's a very high temperature. So it is something like our conventional organic Rankine cycle. So for information, the maximum temperature what we can provide to the organic Rankine cycle is 540 degrees Celsius, right? So that kind of efficiency, that means that will lead to an efficiency about 35 to 40%. That is also possible to achieve by using this technology like heliostat field collectors. Now these are the devices for solar thermal collections. It may be liquid flat plate collector. If your temperature requirement is about 40 to 90 degree, then you can go for this kind of collector. Then evacuated tube, you can go beyond 100. Then solar air heaters, then cylindrical parabolic concentrators if your temperature requirement is up to 400 degrees Celsius. Okay, and then paraboloid concentrating collectors, it can go beyond 400 degrees Celsius. So it is maybe 600 degrees Celsius. So there are some of the snapshots of those technologies. So what you can see at the bottom, it's a central power receiver system. So you have a pole here. At the top, you will have absorber, and along the periphery, you will have all the heliostats. So it's a glass kind. Solar radiation falls, it reflects to the receiver. So from all sides it comes, it receives at the receiver at the top. So from far, what you will see, it's like a milky white substance. It's a very intense heat is generated, right? And then molten salt is actually pumped. It's cold molten, and heat exchange will be there, and it's come down and heat exchange with water and produce steam and then produce electricity by using Rankine cycle. So that's how it works. And the other one, what you see, it's a parabolic trough. So this is the concentrator and absorber at the center. So it's a concentrator, something like that, and this is the absorber. Okay, solar radiation comes, strikes, and then reflect to this absorber, and then heat transfer flows through these tubes, and you can collect in the other side, and then you can use it both in thermal as well as electricity generation. And these are thermal applications. You can use it for water heating, space heating applications, maybe power generation, then distillation is quite a good thing. Like, no, you need distilled water. Suppose if you have a solar power plant and you are using batteries, so you need distilled water. So distilled water can be produced by using this distillation. Your requirement is not that much, so that water you can feed it there, and that will work for the batteries. And more extensively, drying. In the last lecture of mine, I will include something about drying, what interesting things can happen and how we can design a collector for harvesting solar energy. And then cooking. So there are some of the snapshots of drying, and this is something like a desalination unit. There is a glass cover, solar radiation falls, and then water evaporates. Then since the temperature of the glass is lower, it condenses and you can collect at the end, and this is distillate actually. And you can see this other arrangement like what is called Schaeffler cooker. It's quite effective in some of the places. Okay, so solar radiation falls, and then you have a cooker at the focal point, and you can heat it and you can cook it. Okay, but these conventional box cookers are not that efficient. But when required, suppose you are in desert, middle of the desert, you don't have anything to cook. So you can carry those box and you can cook food, and it's done. It can be done. Okay. So we can have concentrating collectors and non-concentrating collectors. So solar radiation is converted from a large area to a small area using optical means, and this falls under concentrating category. And in concentrating collectors, we need beam radiation. So we'll see slowly. Once I complete this part, then we'll enter to the radiation. What are different radiations we need? So it's just for your informations, we have two primary classes of radiation. It's normal radiation and diffuse radiation, right? Of course, we have to account sometimes reflected radiations, right? So these normal radiations are more important in case of concentrating collectors, okay? But both beam radiations and diffuse radiations are applied in case of non-concentrating collectors, okay? Because intensity of diffuse radiation is lower. I'll explain by its character. And the diffuse radiation has no unique direction, and so does not obey optical principles. and that's how we cannot concentrate diffuse radiation in a concentrator. Okay. And for concentrating collectors, the primary advantage is we can generate high temperature because of this optical means. Okay. And also we need to mention three important things about this collector. These are called performance indices. One is collector efficiency, then concentration ratio, and then temperature range. Okay. So collector efficiency can be defined as the ratio of energy actually absorbed and transferred to the heat transfer fluid by collector, and this is nothing but useful heat gain to the amount of radiation incident on the collector. Okay. And concentration ratio, as I said before, can be defined as the ratio of the area of the aperture of the system to the area of the receiver. And this aperture area of the system is projected area of the collector facing the beam. Okay. So for flat plate collector, concentration ratio is 1 because the area of the concentrator and absorber is same. But in case of line focus system, line focus systems are something like one axis tracking, and the point focus systems are two axis tracking. So you can actually track the beam radiation, and that's how we can intensify the radiation, and that's how we can generate high temperature. And of course these concentration ratios are actually related to the temperatures. Now if we talk about flat plate collector, which is a very simple device, and this does not require any sun tracking, and it cannot do also because it's very heavy and you cannot use this collector to track. Okay. So we fix this beta, but this beta is very important. What beta you can see, it's a tilt angle. So what tilt angle you are going to fix? Because see, this earth and sun, they are related. Not always we are exposing to the sun. Okay. So these values will change. Winter will be different and summer it will be different because it is significant. But every day it is different actually. Okay. So if you count n is different, and that's how we get different values for all the calculations. So we'll spend some time for calculation of beta maybe in the next tutorial because it plays a very important role. And this flat plate collector can properly secured on a rigid platform and thus becoming mechanically stronger than those requiring flexibility for tracking purposes. And of course this kind of collectors are always installed in the field, right? So it looks something like this. You have the collector, okay, and then tubes will be there, will come in the next discussion, and then it plays at certain angles, and beta is very sensitive to the time and days maybe. That's how what we do, since it is very robust, we cannot have facility to track, so we fix some beta which is moderate to give a better performance, okay, not the best performance. Okay. This FPC consists of a absorber plate. What is there you can see, this is the absorber plate, okay, and the tube fixed to the absorber plate. These are the tubes. There are different configurations of the tubes. Okay. So it may be something like this. If we say it may be sometimes something like this. So what you have seen here, and sometimes what you will see, this is an observer plate and you will have tubes here, and sometimes your configuration will be something like this. This is the observer plate at the below. Okay. So different configurations you will have. So what you can see, this is this kind. While doing so, actually you can increase the efficiency because, as I said before, this contact resistance. So something you have to apply here. This is normally no pressure bonded. You have some kind of foreign materials to be there, and this actually acts as thermal resistance to the heat flows, right? So can we remove this? So this is the configurations by which we can remove it. Okay. Even though these are very tiny, but its impact is very, very high if you talk about thousands and lakhs of square meter areas of flatbed collectors. Okay. Then you have transparent cover. This is the glass cover. Okay. So how many covers you are going to place over the absorber plate? Is single cover or double cover or triple cover? What will happen if we apply some kind of selective coatings over this absorber plate? So we'll discuss those aspects as well. So if we see this figure, this is quite interesting. This vertical axis shows about useful power, and horizontal axis shows the temperature plate above ambient. So that's why it's TA. This is plate P. Okay, plate temperature. So solar radiation is falling. That's why it is incident. Okay, and this much is absorbed, and there will be some losses, and finally we'll get some kind of collection. So mathematically we'll represent those in the coming slides. And what advantage we are getting here? We are actually utilizing both beam as well as diffuse component of solar radiation. Okay, and only very limited maintenance is required, and disadvantage is collection efficiency is low due to the absence of optical concentrator. So based on our requirement, we can select what technology will be best, and of course we can augment its technology or augment its what is called performance by doing something. Okay. So this is about the absorber plate. So normally this material of construction of the absorber plate is copper. Also nowadays aluminum is used because it's cost. Copper is much costlier than aluminum. Okay, and thickness is about 0.2 to 0.7 mm. You can see its construction, and tube diameter is about 1 to 1.5 centimeter, and tubes are soldered, then braced or pressure bonded. Mostly pressure bonding is done to the bottom of the absorber plate, and pitch distance between two tubes is about 5 to 12 centimeters, and some are already there. I explained it. So here this is the header for cold fluid, and this is the header for the high temperature fluid. So what happens? Cold fluid enters, and since solar radiation is exposed, what happens due to the density difference? Fluid will move from lower to upper, and then this is the cold fluid, and we can store the hot fluid. We can store the hot fluid at the end. Okay. So these diameters, headers are somewhat bigger than the tubes, and that's how it is. Diameter is 2 to 2.5 centimeter. And absorber plate is there to maximize the solar radiation incident on the plate. Okay. So how to maximize the solar radiations? That's the challenge. Can we make some kind of selective coatings? Of course, selective coatings are costly. So this is something like one kind of plastering you can just place over the plate, and that will increase the efficiency of the systems. And of course, how to minimize the losses is the primary things. What mechanism we can apply, and what are the materials we can use to maximize it and reduce the heat losses, and how to transfer the heat as fast as possible. So this cover system it looks a single item. So you see this glass cover, it's not a single line actually, even though it's just I am taking this glass cover, only one glass cover. There are two glass covers are present here. So I am taking this one. I don't know what is it. So I am enlarging this. It is something like this. Okay, this part I am enlarging, small one. So it's actually it is something like this. Okay, and complex things happens here. Solar radiation comes, suppose some amount of solar radiation is falling on the glass cover. This is a glass cover, its thickness, this is a thickness. Okay, it some are reflecting, okay, and then we will have it goes internally, it reflects, it goes something like this, it happens something like this, okay, and then so finally you will get something, some kind of radiation here. So this cover system is something like this, single cover, but it has got some thickness, and what happens inside this, that's what as you're presenting, right. So that's how we need a very transparent, because normally these glasses are represented in terms of extinction coefficient. So it is, if we increase the transmissivity, so this value of extinction coefficient actually varies from 19 to 4, okay, and it's a K and it's a meter inverse, okay. So if we reduce the extinction coefficient from 19 to 4, then you can actually increase the transmissivity from 0.95 to actually 0.97, okay. That impact is also very, very high, even though it looks very tiny, but impact is very, very high, okay. And this cover is opaque to the long wave radiation, okay, and this is a toughened glass, and normally its thickness is 4 to 5 mm, and so that it should able to absorb some kind of thermal shocks, okay. And normally these gaps between this cover and the absorber plate is about 1.5 to 3 centimeter, okay. And sometimes it is also seen that plastic transparent sheets are also used, but its efficiency is somewhat lower, okay. And of course it is originated from fossil based plants, so we don't encourage this kind of systems to be there. We need insulation and collection boxes, like bottom and sides are usually insulated by mineral wool, rock wool or glass wool. These are insulators. What could be the conductivity of this kind of insulators? It's like 0.03 watt meter Kelvin, right. So that range, it's very, very low thermal conductivity, and thickness about 2.5 to 8 centimeter, and whole assembly is contained within a box which is tilted at a suitable angle. So tilt angle, normally if your requirements, say for example you are devising a flat plate collector for a place like Meghalaya, maybe Shillong, or a place like Gujarat, or a place like Paris, okay, then what could be your concern? First thing, for which purpose you are installing. Say for example, if you talk about say Paris, you are designing this flat plate collector. So your target should be why you are installing this, because in winter you are going to get some kind of thermal energy, okay. So that means what you will do, say for example you start with November or December and then end with maybe March. So during that time you are going to operate it. During that time you optimize what beta maximum or beta optimum for maximum energy, okay. Otherwise if you design beta for maybe June, July, August, that might not work for a place like Paris during the winter, okay. That's just the logic, okay. We'll solve some problem, and that is quite interesting. Then this entire collector box is usually made of aluminum with an epoxy coating on the outside for protections, and face area of the collector is normally 2 square meter. And this kind of configurations, as I already said, are available. Now this is a very interesting problems, okay. So if I talk about, it's a 100 liter capacity thermosiphon, because of this temperature difference there is a fluid flow, and we are not using any passive mechanism to flow the fluid, and solar radiation is 5.5 kilowatt hour per meter square per day, okay. It's daily. Then collector efficiency is 52, then absorber area is given, water inlet temperature is given, then specific heat is given, geyser. So we have a geyser and then solar flat plate collector. We'd like to replace this geyser by flat plate collector. Then what benefit you will get? How are you going to solve this problem? So it's very easy, right? So it is something like is mCpdt. So it is 5.5 kilowatt hour. That means we can get 3600 this kilowatt second, okay, and multiplied by area is 2 is the collector area. Then what is the efficiency? Efficiency is about 0.52, okay, which is equal to mCpdt. So what is m here? 100 liter is 100 kg. It's clear? 100 liter is 100 kg because density is 1000 kg per cubic meter, right? So from that we can say it is 100 liter is 100 kg. So it is 1000 m. Then Cp is 4.18. Then you will have delta T is to be calculated. So if you have calculator, you can find out what is delta T. Okay. Once you know delta T, then what you can find out what is the outlet temperature. Then outlet temperature will be this delta T plus T1. T1 is your ambient temperature is 23. This part is your 23 degrees Celsius, right? So if you calculate, so T2 what you will get is close to 72 degrees Celsius. Okay. So this T2 will be 72 degrees Celsius closely. Okay. So again, once you know this geyser efficiency and also you know the solar radiation, this is 5.5 multiplied by what you will have is 2 and an efficiency is 0.52 and its geyser efficiency is 0.96. So this will give you the daily energy, say because this 5.5 is daily energy. Okay. So if you calculate, you can find out a value. You can tell me what value you will get here, and this will be per day energy savings. So if you multiply with 30, then what you will get is a monthly average values. So I have I have done the calculations, and it is about 35.7 rupees. It is 35.7. This is Indian rupees per day. Okay. So if you need for 1 month, you need to multiply with 30. So it is about 1000 rupees, right? So it's a significant save. In 1 year, you will get 12,000, close to 12,000. So that's a really interesting saving. And payback period maybe 2 years you are going to get it. So this is quite practical, and you can find out these parameters. And also you can verify. So there is charts already people have prepared. So how this will behave. Sometimes if you don't know anything, but you want the solution, what kind of technology you are going to use to utilize if you have a temperature of 400 degrees Celsius. So you just go and there you see where is the cross section, then you can find out what the efficiency and what are technology you can use it. Okay. It's a very user guide for choosing a right collector at right temperature. Also now, this is quite interesting. So what really we are interested at the end, the amount of heat you are going to collect, that is useful heat gain. This is QU. So as I said before, if you could reduce this QL, okay, and also here you can increase, then you can actually gain more. Okay. Now our attempt is to find out what is S and what is QL, because this is known to us. Then we can find out what is useful heat gain, right? So this S, even though it looks only S, it's not so simple. Actually, it has lot of components, right? So this S is nothing but the incident solar flux absorbed in the absorber. So this is not something like I, because you have glass cover, then you have absorber plate, right? Then you will have all those tubes, and then you will have all insulations. So these all are insulations. Okay. So I am talking about this S here, amount of solar radiation absorbed in the absorber, and this IT is the total amount of radiation which is falling on the glass cover. Okay. So this S is also a function of IT. Okay. So slowly you learn this flux incident on the top cover is something like IB, RB. IB stands for beam radiation. RB stands for it's a parameter like what way your system is placed. It is at certain angles with respect to the horizontal surfaces. Okay, it's a tilt. Okay, so this is diffuse radiation. This is that coefficient term plus ID RB plus RR. Okay, this is reflected radiations. Okay, this is for diffuse radiations. So this flux which is absorbed in the observer plate has got this kind of expression. So now what you need, of course you can find out this IB by using a device called pyroheliometer, okay, and then ID by pyranometer. So these values can be found out, and we have appropriate mathematical expression for finding out these RB values. I will tell in the coming slides. And problem is with this tau and alpha for beam radiation and tau and alpha for diffuse radiations. So how to find these values? So now let us see how we can find it. And this term tau alpha beam, which is the transmissivity absorptivity product for beam radiation falling on the collector, and this is for diffuse radiation. Now for transmissivity of the covert systems, we want this tau, and then this tau is a function of tau R and tau A. Now we are entering somewhat in complex system. Okay, this tau R is transmissivity obtained by considering only reflection and refraction, and tau A is transmissivity obtained by considering only absorption. Okay. Also we have beam and diffuse radiations. So both the things need to be treated differently. For finding out tau R, we need to analyze this Snell's law. Okay, it is transmissivity based on the reflection, refraction, and Bogart's law it's a transmissivity based on absorption. Okay, and then we will go for diffuse radiation. So what condition we can use it for diffuse radiation, that also we will study. Now if we see this Snell's law, if we have an incident beam radiation, if theta 1 is the angle of reflection, incident sorry, and theta 2 is the theta 1 is also the angle of reflection, and refraction is theta 2. So this angle of reflection or refractions can be related with these expressions. Sin theta 1 by sin theta 2 is equal to n2 by n1 if they are of different mediums, right. This is the refractive indices, right, and this is also related with the rho, which is nothing but reflectivity of two component of polarization. Okay, it's a light, it's a polarization. So it's a polarization. Both sides it happens. It's something like this and other side. And the two components of polarizations we need to take care. This is represented something. We are not going to derive these expressions. We need to consider. We have to stop somewhere. Okay, so these are the two expressions, and for normal incidence theta 1 will be 0, and we will have this expression. Okay. Similarly, we can go for transmitted tau R expressions, and we can find out tau R by averaging this two component of polarization of transmissivities, tau R1 and tau R2. Okay. So once you are done with this tau R, then we can go for tau A. Okay. And for this, as I explained before, so radiation comes here, it goes back and transmitted, again it reflects internally, and then some of the radiation goes out. So what really we want, this is the sum. This much actually contributing to the heat effect, right? And that's how this is the infinite series, and we can sum it, and finally for n number of coverts we can develop the mathematical expression for tau R1 and tau R2, because you don't know how many coverts are required to optimize the performance. Okay, so that's how we can get the expression. So m stands for number of coverts. Now we'll go for transmissivity based on absorption, and this is obtained by assuming that attenuation due to absorption is proportional to the local intensity. Okay, So, this Bogart's law says di is equal to minus ki dx. Okay. So, if you take like di by di minus kx and integrate, because this is the cover system. Okay. This is a single cover you see one line, but this is expanded thing, right. So, delta c is the thickness of that cover, and then we have taken a small segment out of that, and this is the radiation takes place, and that is how 0 to delta c is the integration. So, if you do the integration, then what are you going to get is tau a e to the power of minus k delta c, and this k is nothing but extinction coefficient. Okay. So, its dimension is so it is meter inverse, okay, for glass, and yeah. So, that is how we can get this tower. So, if you do the integration, and then it will be tau a to the power of k delta c, considering that it is falling normally. So, if this radiation entered at certain angles, then what will happen? So, that condition also I have reported. So, when the beam is incident at an angle of theta 1, okay, with the normal to the horizontal surface, the path travel through the cover would be delta c by. So, you can immediately find out what could be this theta, because this theta 1, theta 2, and then if you take a b cos beta, it will be delta c, and from that you can find out what is a b. Okay. So, if this is the case, then you can do the integration and you can find out finally what is the expression for tau a e to the power of minus k delta c by cos of theta 2. So, if you know this theta 2, then you can find out what is the tau a. Okay. So, that means you know tau r, how to calculate, you know tau a, so then you can find out what is tau, right. So, it is very easy now. So, that is how we can, I have formulated one problem, it is solved problem, I will show you in the next slide. So, now that is done for tau. So, what will happen tau for beam radiation, what will happen for diffuse radiation, that is the concern now. So, what will happen for diffuse radiation? This diffuse radiation is equivalent to the beam radiation coming at an angle of 60 degree. Okay. So, this angle is arrived at by considering the variation of transmissivity and by assuming that the amount of diffuse radiation coming from all the direction is same. Okay. So, let us take a example. So, we are going to plot the variation of tau r, tau a and tau, that is the example. So, material we are considering glass, and number of cover we are using 2 covers. So, glass cover 1, glass cover 2, then we have absorber plate, and then you have tubes and other things. Then thickness of each cover is 4 mm. Reflective indices are given, relative to AR is 1.52, and extinction coefficient of the glass is 15 meter inverse. Okay. We need to find out all values, and we need to generate this kind of plot. Actually, you will get this kind of plot. That is why in 60, the radiation what is coming at 60 is equivalent to like diffuse radiation. Okay. So, now this is the calculations I have done. So, what is rho 1, what is rho 2, and then tau r1, tau r2, okay. And then finally you find out what is tau r, because tau r is the important thing we need to find out, and then we need to find out what is tau, okay. And for that actually we need to find theta 2 as well. So, we can actually take different angles. Just I have shown only one what is called angle at 30 degree. You can consider at 15, 30, 45, 60, then 90. Okay. Then you see what kind of plot you will get. So, it will be something like what I have shown, this kind of plot you will get. Okay. So, all are converged at 90. Okay. It will be at 0, right, at 90. So, this kind of plots you can generate. So, if you are very excited to see, really you can do it, it is very easy. So, you can take a snapshot and you can do the calculations for other angles, maybe a spreadsheet you can use and then do the calculations anywhere you can generate the plot. Okay. So, these are very, very important aspects, and this is really important if you can correlate with the performance of the system. Okay. And also sometimes this product we call it as transmissivity absorptivity product is very significant, that is defined as the ratio of the flux absorbed in the absorber plate to the flux incident on the cover system. Okay. So radiation falls, this is the cover, this is now absorber plate, this is now absorber plate, and this is your covert system, right. So now covert system is only single line. Earlier what happened, we have expanded it, it is like a single line now. So this is transmitted and then again it goes to the tube. So these are like, it is going to the tube after absorber plate, right. So that's how this is very, very important. And net fraction of it is absorbed, it's an infinite series, you can sum it, and if you sum it then you will get this expression, right. So for diffused, this is diffuse reflectivity of the covert system, it is 0.21 for two covert systems and 0.15 for single covert system, okay. And this rho d can be found by determining the values of tau a 1 minus tau r for the covert system for incident at an angle of 60 degree. So that means we know all the parameters now. So for diffuse as well as beam radiation or direct radiation, right. So this is the very important informations, and also you must remember what is S now. So what happens, we have done this tau a, tau alpha for beam, tau alpha for diffuse radiation, then we can find out S, because already we have calculated the IB and ID by using those instruments, or if you don't have the instruments, of course we have to use for some kind of correlations, right. And this RBR is mathematical expressions, we can use those expressions and we can find out those values. So that means we can now calculate what is S, okay. So once we know S, then what is next, we need to find out is QL, this losses, okay. This is very, very important. Right now you can play the game, that means if you increase or decrease the transmissivity, then what will happen, okay. As I said, its transmissivity if you can increase, okay, that means extinction coefficient from 19 to 4, actually we can increase the transmissivity from 0.95 to 0.97. That's really impactful result you can get if you do this. Now we will calculate the losses, okay, then we can find out what is the amount of useful energy you gain. So energy balance if we make on the absorber plate, this is the absorber plate now, solar radiation is falling and this is the top losses, side losses and bottom losses. So this is the plate temperature. Normally this temperature is unknown and it's very difficult to know. It is inside, you need to have a lot of thermocouples and this is non homogeneous, okay. It's really very, very complex, but there are some expressions to find out this QU in terms of fluid inlet temperature. That is called Hotel-Wheeler Bliss equations, Wheeler-Bliss equation. So that equation we use to find out this QU. But for your understanding, you must know how this can be calculated, okay. So this S is known because already this part we have done. Now our things is QL. So once you know now this one, then immediately you can find out what is QU, okay. So this heat loss from the collector can be mathematically expressed as UL AP TPM minus TA. TPM is the plate mean temperature and A is the ambient, TA is the ambient temperature, and UL is the overall loss coefficient, okay. And this QL actually sum of all the losses, it may be from top, it may be from sides, it may be from bottoms, okay. That's how we can say this heat loss from the collector is the sum of heat loss from the top, bottom and sides, and mathematically we can represent something like this. And this can also be expressed in terms of loss coefficients, okay. So this, how this can be expressed in loss coefficients, rate at which heat is lost from the top is something like this, UT, then this for UB is for bottom and US from the sides, and these all are constant now, and this is also constant, we are considering constant. So if we sum it, it will be something like this, okay, because these are constant, so this will go each other, and finally also we can find out the loss coefficient will be your UL is UT plus UB plus US, okay. So now if you know these losses, then you can find out what could be your QU, and also you can give a check. If this value falls between 2 and 10 watt meter square Kelvin, then your design is okay. And if it is very, very close to 2, then you can say you have done a very good design. And if it is more than that, no, your design is somewhat not good. Okay. So this is a set point, like no, okay, this value is in between, then you are done, because you need to do lot of calculations. I will show in the tutorial part. And these losses can also be drawn, like no, you have studied in heat transfer, like no, once you have a slab, and then you can consider it like a resistance, like it's like a Ohm's law, analogous to the Ohm's law. It's temperature difference and potential difference, and current flows and heat flows. Okay, so it's analogous to the Ohm's law, or Ohm's law is analogous to our thermal resistance. Okay, so that's how we can write something like this from TPM to ambient. It is from sides, from bottom, and this is from top. Okay, and this can be again redrawn to represent equivalent the resistance network. It represented something like this. Okay, it take care of all the losses, okay, what we have represented in the last slide. So now we will represent the situation to know or to estimate the top loss coefficient if we consider 2 cover system and a plate. Okay. So what happens, solar radiation comes and strikes on the observer plate, and then it goes up. Okay. We will also explain how radiation propagates from sun to the earth surface very clearly. Okay. But here in this case, what happens, solar radiation comes and strikes on this glass plate, and then it goes up. That means what we can say, this TPM is more than TC1 and TC1 is more than TC2. Then you have T sky. Okay. What is T sky temperature? Do you have any idea? What is the difference between ambient temperature and sky temperature? So sky temperature is something like when solar radiation comes, okay, what happens, these emissions or radiations are trapped in the gas molecules, and that emits the radiation, because any objects having temperature more than absolute 0 will emit thermal radiation. So that actually retains heat and it emits radiation, and radiation exchange takes place from one object to another object. It is not ambient temperature, actually it is exchanging heat from the glass cover to the object, that is like gas. Okay. So this is like T sky. That is why when we write very precise mathematical expression for radiation by using Stephen Boltzmann's law, we write always T sky, not the ambient temperature. Okay. So ambient temperature is for convection, not for radiation. Okay. So that is how what we can say here, but you must remember one strategy, this TPM is always greater than TC1, is always greater than TC2, and TC2 is always greater than T sky. So this actually help you or guide you to solve some of the important problems which I am going to study in the next tutorial section. So we will have this heat exchange from plate to glass cover 1, then from glass cover 1 to glass cover 2, then glass cover 2 to ambient. Okay. So this has been something like this. So from top to QT divided by AP is HPC1, this is P to C1, TPM minus TC1, and then there will be radiation exchange between the plates, this plate and glass cover. That is how, and this is radiation parameters, because how these plates are view each other. If they are in parallel, then we can use this expression. Okay. If it is enclosed surface, the expression will be different. If it is spherical, then things will be different. Okay. So since these plates are parallel to each other, then we can use this expression, right? It is a radiation parameter or view factor, you can say. This P is for plate and this is for collector. Okay. And these are unknown. We need to know what is called assume those values. And then from first cover to the second cover, distinction, second cover, third cover. But this has to be same for all. This expression 1, if you say this is 1, this is 2, this is 3, this QTAP has to be same for all. Okay. So, that you should remember when you are solving these expressions. Suppose if you consider any temperature and solve it, if you found different values, then your choice is not perfect. Then you need to redo the calculations until and unless you get a very close value of Qt by AP for all the expressions. Okay. And for this kind of situations, I am not giving a lot of correlations, heat transfer correlations for finding out this heat transfer coefficient, because from glass cover, from plate to the glass cover 1, these are all parallel, and you need to find out what is Ra cos beta. It's a Rayleigh's number multiplied by cos of beta at what angle it is located, this tilt. Okay. So, if the range is in between these two values, then you will use this, and if it is in these two values, then you will use this expression, and then similarly in the last expression. Okay. But this properties to be evaluated at the arithmetic mean of the surface temperature, because mean temperature. So, this glass cover 1 and this is maybe plate and this glass cover 2, right. So, here you know this temperature, say for example, this is TPM and this is TC1. So, what happens, this is air, okay. This air temperature is different, right. So, what you need to find out, what could be the properties of air at this portion, it will give you at a temperature of TPM plus TC1 divided by 2. At this temperature normally we take the properties of air, then you can do the calculations for heat transfer, and this expression, this correlations will give you heat transfer coefficient, because this Nusselt number is H and this is characteristic length will be your this length, okay, not the diameter here and not this way, this is the way heat is exchanging. Okay. So, which way heat is exchanging? Of course, it is from observer plate to the glass cover in the vertically up. Okay. So, that is how it is L, okay, HL by K, that direction, because heat is flowing from this direction, and that is how we should consider L here. Okay. That means thickness, and then you can find that what is H plate to C1 one case, and other case it's C1 to C2, and then accordingly you can find out other heat transfer coefficient. Okay. So, we can also use these correlations for finding out HW. HW, what is HW? If you go back, this is HW. So, when we have heat exchange from TC to the ambient, then we need to use this HW, right. So, this HW already correlated by many researchers. So, that is how we can find out this HW is 5.7 plus 3.8 into U. U is the velocity of wind, or at what velocity particles are moving there. Okay. If you know that, then you can find out, and either of the correlations can be used. And as I said, this T sky and TA are related. Macadams, they have correlated that this T sky is about 6 degrees lesser than ambient. It is TA minus 6. Okay. So, that is how we can take this sky temperature is TA minus 6. And once that is done, that is for top. So, now we need to find out for bottom and sides. So, for sides, if you know this conductivity, thickness and conductivity of the insulations, then you can find out what is the bottom loss coefficient, and this is by considering convection losses from absorber plate towards the downward direction. Okay. Its bottom loss coefficient can be find out according to this expression. And for side loss coefficients, because there are many sides, okay, you have these two sides and 4 sides you have of different dimensions. Two of the dimensions are same, and that is how we can get this area, and we can do this is as a mathematical calculations, and we can find out what is US if you know the dimension of the collector. Okay. So, this is dimension, this is L1 and this is L2, and you know the temperature difference here. Okay. So, this US can be calculated. That means you know now what is UT, what is UB, and what is US. That means you know now what is UL. That means you have started with something like no QU. So you need to know this QU, and then this term, that energy what is absorbed minus QL, and this QL is nothing but no function of all these losses. So you know all the parameters now. Then you can find out what is QU. So that is done. Okay, that's how we can design a flat plate collector. Okay, now also we need to discuss two very important parameters. You are confident that you know this expression and QL, then you can find out what is QU. Now we are going to calculate this instantaneous collector efficiency. What could be the collector efficiency? Okay. So this collector efficiency, or normally in solar calculations we consider 1 hour is instantaneous, not in 1 second. Okay. So because we consider that in 1 hour this radiation is not going to very much. So that's why we consider 1 hour time is instantaneous time. So this is useful heat gain to the radiation incident on the collector. This QU by AC IT. Okay. Because AC is the collector area and IT is the total radiation which is falling on the collector, and QU is the useful heat gain, right. Now you also need to know this AC and what is the relationship between AC and AP. AC is the collector gross area and AP is the plate area. Okay. So this AC is something like about 15 to 20 times more than AP. Okay. That's how we consider 1.2 times more than AP most of the cases. Now we are going to select the material, which material will be selected for your application. What is the basis of selection? You must know up to what temperature your system will work. That's the first thing, right. So in order to study that, what we do, normally we study a temperature called stagnation temperature. That's the maximum temperature a solar flat plate collector can provide. Okay. So how do you understand that? You fix it in a particular place, that flat plate collector, and don't take the heat out from the system from morning to the evening, maybe at 4 o'clock, and you see what temperature you will get at 4 o'clock, and that is nothing but your maximum temperature or stagnation temperature when you are not utilizing the heat. That means QU is 0, right. So if QU is 0, then what happens? So you know expression for this, then QU is 0 means loss QL is be APS. This is the condition at which you will get the maximum temperature, and this temperature is very, very important for designing a solar collector. Okay. So that's how I said is useful as an indicator for comparing the different collector design. Okay. And it is useful for construction of a collector. So these 2 points you should always remember as far as collector design is concerned. Okay. Now we know how to evaluate. Now more complex things will come now. Okay. So this is just an example. So if I go provide this top loss coefficient, because investigating top loss coefficient is more complex, and I am giving this value, and immediately you can find out other values. If I know the thickness and then insulation and then size of the collector, then we can find out what is US, and finally you can find out what is UL, and that takes about 7.57, which is less than 20 watt meter square per degree Celsius. That means it is well designed. Now so far the expressions what we got is QU in terms of TPM, plate mean temperature. Okay. So which is very, very difficult to find. So we need an expression which will give you QU in terms of fluid inlet temperature. So how to do that? So in order to do that, so we need to analyze two important parameters. One is called collector efficiency factor, and other one is collector heat removal factor. Okay. So you got this information already. You are aware about it. If you have two glass cover and then one absorber system, right? And also we can draw this kind of thermal resistance. Okay. For if you are doing very microscopic analysis, then this will be something like this. Okay. So, this is the temperature profile. What happens? This is your absorber plate and you have attached these tubes. So, heat transfer fluid is flowing through these tubes. So, what happens inside? So, this will be fixed at constant temperature and then there will be rise and then this will be something like this, and your tube is here and this tube is here. That means it is not so, it will gradually it will go something like this. Okay. So, in between there will be temperature rise. So, it is something like this is x, that is why I say this is x, and along the length it is y. Okay. So, along the x your variation will be something like this, and along the y, suppose if you consider this tube, so this is at TFI fluid inlet temperature and outside what will go out is TFO. Okay. So, if we take a plot in a y direction, so it will be something like this. Okay. So, temperature, inlet temperature will vary from inlet to outlet, but in between the tubes you will have this kind of temperature profile, right. So, now we consider a small segment and do the analysis and see how this can be calculated. So, these are the expressions. First, let us define what is collector efficiency factor and heat removal factor and why we are doing this. So, why we are doing this? Because we would like to establish a relationship of something like this. So, TFI. So, earlier QU was in terms of TPM, which is very difficult to know. Okay. So, this TFI we need to know, always we know like TFI inlet fluid temperature is like ambient temperature, this is known. So, it is very easy for us to calculate, but what is FR? So, collector heat removal factor is defined as the ratio of actual useful heat collection rate to the useful heat collection rate which would occur if the collector absorber plate are at the temperature of TFI everywhere, and its value is 0 to 1. Okay. So, higher the value, better is the good, better is the performance. Okay. Okay. And also we can actually define this FR, we can actually derive the entire things, and something I will derive, and but I am not going to solve it here, but I will just show you the mathematical expression how this can be done. Okay. And the collector heat removal factor is similarly, but this we are maintaining at the temperature of TF, and it values varies from 0.8 to 0.95. Okay. But you must know why we are doing this. Okay. So, that is how we can consider a one dimensional flow of heat in the absorber plate in the direction of at the right angles to the direction of the heat fluid flows, and heat flow from the plate to the fluid across the wall, and one dimensional flow of fluid inside the tube. Okay. So, these are the considerations for our calculations, and then if we take a small segment, this is the segment, this is in between the tubes and dy is the other side perpendicular to the board, and then we can do the energy balance and see what happens. So, you can get this kind of expression. I will share those documents, you can just read it, that is not a big thing. Just we have considered one single element and apply the energy balance, and finally, we got an expression of something like this, and we will just show the final results, and this is in between you will get these results. I think I missed one thing. Okay, this is for n number of tubes, and we can do it. Okay, okay. Later on we will get the expression. So, for collector efficiency factor, what advantage you get? So here this is the absorber plate, and you have applied or you have given some foreign material inside whose thermal conductivity is different than the material here and here. Okay. So, you need to consider the thermal resistance offered by that material. Okay. So, if we make a single material, then it is always good, then we can actually discard that thermal resistance offered by that material. That is the one novel collector systems you can thought of. And for our analysis, what we did know, this tube wall, the resistance offered by the tube wall we have not considered, and we have done the analysis, and see what we will get at the end. We will get an expression of something like this if configuration is something like this. Just below we have attached this tube, then QU will be FDES, APS. This FDES is nothing but collector efficiency factor, and this expressions you will get, and this is in TF. Okay. And for different configurations you will have different FDES. So here you can see inline we will actually consider, we will discard these losses, what is available in case of tube bonded above the absorber plates. Okay. So that is how this is not there, one portion is not there, this part is not here, delta by this part is not here. So that is how we can get some kind of higher efficiency in this configuration. So collector heat removal factor I can get. So these are some of the calculations you can see, because we cannot discuss all these aspects here, but I will give the informations, you can just do the analysis. And finally what you will get is this one, FR and QU. So QU, what you get, FR APS minus UL TFI minus TA, and this FR is something like this. And what is the significance of this? This is a design parameter, since it is a measure of the thermal resistance encountered by the absorbed solar radiation in reaching the collector fluid. So it is like one kind of design parameter. Okay. So lower the value of FR, then higher is the efficiency, right. So how we can do it, that's our concern. Okay. So then once you can calculate this FR, then you can actually find out what is QU, because all the parameters are known to us. We do not have to think about TPM, it is TFI. So why this TPM is so interesting, when you solve this problem in the coming slides, then you realize. But you must know what is FR and what is the physical significance of FR. And once you know these other parameters, then we can find out instantaneous efficiency, and throughout the day what is the efficiency. So it's very easy now, all the parameters are known. And sometimes since we need to find S, so it is very difficult to find RB, RR and individual IB. So what we do, we just know this IT and then we multiply with tau alpha average. So tau alpha average will take care of both beam and diffuse radiation. That is easy for us to calculate. Okay, this is an example. So this shows an FPC has an aluminum absorber plate, and Kp is given and thickness is given, an area of 1.5 square meter, and it has two riser tubes, each of diameter 0.025 meter, and length of the tube is given to you. We need to determine the collector efficiency factor FDES for this collector if the convective heat transfer coefficient from the inner tube surface to the water is 50, 100 and 200 watt meter square degree Celsius, and overall heat transfer coefficient is given. If you do this, then for different cases you can have different values of FDES, and from these calculations what information you can actually take. So as you go on increasing this H value, you can actually increase this FDES values. Okay. So what does it mean, like if H value means what? Heat transfer coefficient, heat transfer coefficient more, that means you need to spend more energy to increase the heat transfer coefficient than from passive to active. Okay. So in expense of some amount of energy, you can actually augment the efficiency of the system. And also you can see, so now similar calculations, but what I said, I change the material from copper to galvanized iron. See what will happen. So these all are very, very practical, because you are going to build, you are going to design a system. What will happen if you change the material? What will happen if you have different convective coefficients, or maybe heat transfer coefficient? Okay. So these are all design aspects. So you can find out what is add this for this situation. Okay. And also these flat plate collectors can be connected in series, parallel and mixed. Suppose if you stay in a hostel of say capacity 1000, okay, and then if I ask you to design a flat plate collector, then how you will design? What is the design basis? Okay. First, what you need to do, you need to know the amount of heat to be given and then at what temperature. Okay. So, you see like these FPCs are connected to increase the volume of water to be heated. So, if first series means what, its parallel means what, one after another, right. There is a header and at the top you have a header. Then what happens? All are at same temperature. All are at same temperature because they are in parallel. Series means what? So, you feed it here and then you take out, and that inlet will be outlet will be inlet to the other, and then you take out, and that outlet will be inlet to the others. So, that is the series connection, right. So, in parallel connections we are promoting to increase the volume of the water, okay. But in case of series connection, what happens? Outlet of one row of FPCs is connected to the inlet of the second one of FPCs, and that way it will go on. And while doing so, what happens? Mass flow rates are same for all, and the outlet temperature actually increases. Okay. So, in series connections you are increasing the outlet temperature, in parallel you are increasing the mass flow, right. Now, if you need to meet the demand for 1000 students in a hostel, then what could be your design basis? So, you see this first FPCs are to connect in the parallel for given capacity of hot water to make one row. How much do you need is quantity, okay, in parallel first. Then you make it series, then maybe you can see parallel, then that way you need to design. Okay. First you make the arrangement for requirement, then you go for doing this. So, this is very very interesting. So, then modules are connected in series to increase the temperature as per the requirement. And you must know this FPCs of this mixed mode will operate in force mode only. That means you need to spend some kind of pumping power, okay. You need to spend some amount of energy, right. So, this is interesting again as far as design of FPCs are concerned. Now, you see the configurations of parallel plates. So, this is water in header, and this is hot headers, and outlet, from outlet you can store energy, right. And this is like mixed or combined FPCs, okay. So, these are connected in parallel, then it is series, okay. Then you just go on doing it based on your requirement, because in a single system you cannot do it. You have different lobbies and different terrain. So, you just use the particular terrain for a particular set of people, and then you design for other people's, because at a time if you connect, then it will be some of the operational difficulties you might arise while designing. So, this is one way of designing a flat plate collector. Now, what are the parameters it influences the performance? It's like design parameters, then we have operational parameters, meteorological parameters, then environmental parameters, right. So, some of the prominent parameters includes selective surfaces, number of covers, cover tilt, transmissivity, inlet temperature, dust on the top cover, spacing and shading. These are the important parameters. These are also falls under design parameters. Selective surfaces, it is very interesting material. Still, if you see in the Google or maybe Science Direct, you will get lot of papers on these selective surfaces, because it's a some kind of layers you are laying over a observer plate, and you are increasing the efficiency of the system. Okay. So, observer plate surface which exhibit the characteristics of high value of absorptivity for incoming solar radiation and the low value of emissivity for outgoing radiation. Okay. So, these characteristics must have. Also, you see, if a surface that has a high absorptivity for wavelength less than 4 microns and the low emissivity of wavelength greater than 4 microns can be prepared, it would have the characteristics of desirable for an observer plate surface to act in the selective fashion. Okay. And there are different methods of making it. So, but you see this is very, very thin, it is like about 1 micron is the thickness. So, one of the commercially available selective coating is Sarmens, and it consists of fine metal particles in dielectric or ceramic matrix or a porous oxide impregnated with metals. Okay. And thin film of those composites are transparent in the high wavelength region and strongly absorbing in the solar radiation region. Thus, they may be they form a stable surface when deposited on the highly reflecting metal surfaces. Okay. And you can see this absorptivity, you can increase from 0.8 to 0.99, and then emissivities can be reduced in these cases. So, now you can see some comparison. Hope it is not boring, right? Everything is all right? Yeah. Okay, let me drink water. So, we will finish it. Once it is done, then radiation we will take and then we will finish it. So, selective surfaces, if we talk about this selective surface, non-selective surfaces. Okay. So, first case we have considered absorptivity 0.94 and emissivity 0.14. You can see the efficiency is 43.6. Then there is no selective surface, efficiency is 31.5. And then selective surface with enhancement of absorptivity and no reduction of emissivity, 45%. So, you can consider 31 to 45% rise. It is really, really significant, right. So, this is one observations. Then we will have selective surface with number of covers. So, this is the selective surface, and then we increase the cover from 1 to 2, then 2 to 3, and you see what happens. Selective surfaces with single cover is having higher efficiency. That means what? We do not need to increase or invest for buying additional seats. Okay. So, this is not required, right. So, this is sufficient. So, selective coating with single cover is fine. Now, you see non-selective surfaces, we have first 1 cover, 2 cover and then 3 cover system. So, what happens, as you see the efficiency, this 31.5 with single cover, 35.2 this second cover, 2 cover, that means, and if we apply 3 covers, then it is 33.4. That means what? It is without selective surface, what we will have? We will have higher percentage of conversion in case of 2 cover system. Okay. So, with selective coating, single cover and high efficiency, without selective coating, 2 covers and efficiency is lower than selective surfaces. So, it is quite effective to have a selective surface. Now, tilt. So, at what tilt? As we have discussed many things about tilt. So, we have got a lot of expressions. So, this is one of the famous expressions, which is annual insulations, how we can calculate. So, this, even though it looks somewhat complex, but that it is not that complex once you start with the calculations. We will actually go back and we will show how this expression could be arrived. So, this relative annual insulation is the ratio of the annual insulation for given values of phi and beta. Phi is longitude, right? Sorry, longitude, latitude of the place, and then beta is the tilt, and if it is 0 for both the cases, then what could be relative index? Okay. So, for winter, the recommended value of tilt is phi plus 10. Phi is, so you know how to define latitude. So, suppose this is the globe and your equator is here, right, and this is the prime meridian maybe. So, if we consider a place here, okay, and what you do, you take the radial line, you connect the center of the earth and the place, the angle it makes with the projected equatorial line is actually phi. Okay. So, this is actually latitude of the location. So, you take the place and then connect to the center of the earth and makes an angle with the projection on the equatorial plane, it is phi, right. So, if we for winter they consider phi plus 10 or phi plus 15 is fine, for summer phi minus 10 and phi minus 15. So, it is significant, right, it is 30 or 20 degree difference. So, it impacts a lot, it is very, very crucial to have understanding on it. Okay. So, this for finding out this average or monthly average values of energy falling on the collector plates per unit area, then we can use this expression, and this is monthly average altitude angle at noon. Okay. So, you can find out this flux which is represented here, and in order to find this we can differentiate this beta and equal to 0 and then find out what is B optimum. Okay. So, this B optimum will be something like this. So, it depends on this particular habit. We will solve one problem in the next tutorial session, then your things will be clear to you. Okay. Spacing also important, and what spacing is appropriate between this glass cover and observer plate. So, this also plays an important role, and because it is related to heat transfer. So, it actually if you take a certain heat transfer coefficient and its temperature and then delta T variation, it will be something like this actually. So, this is spacing, So, it says about 4 to 8 centimeter is always good for to have the spacing, because it's a relation between space, it may be about 1 centimeter, then and here it is maybe 8 centimeter, something like that, and this is Nusselt number or heat transfer coefficient, it goes something like this. So, normally 4 to 8 is preferred for this kind of configurations. And also for inlet temperature. So, as you go on increasing the inlet temperature, actually you are reducing the instantaneous efficiency. What happens actually, decrease in efficiency is because of the higher temperature level at which the collector as a whole operates when the fluid inlet temperature increases. So, as a result, this top loss coefficient is increases and instantaneous efficiency decreases. Okay. Then we will have transmissivity, as I said, this impact a lot. So, if you can reduce this transmissivity from or K value from 19 to 4, you can actually increase the transmissivity very effectively, and that's impact the performance very significantly. Dust is also important. So, normally what the kind of discussions we make is like every day we are cleaning the solar module, but it is not possible, right, every day cleaning the solar module, it is really not possible. So, periodic cleaning maybe twice in a month is also fine, so in order to have good performance. So, once you do this, then really you will get a very good performance, otherwise you need to multiply with some kind of correction factor, because the calculation what you are doing is for always clean. Okay. So, correction factor may be 0.9 to 0.99, you can multiply with that. So, these are some new development like convective losses, how you can reduce it. Okay. So, that's the attempt to reduce the heat losses and to improve the efficiencies. Okay. So, I will not spend much time because you are a little bit bored, but I will make you engage in other calculations soon. Okay. So, this is like the further development what people have done, like evacuated tube collectors to reduce the convective losses, so that you can increase the efficiency. As I said, if you fundamentally correct, then you can do everything. QL, if you can reduce this QL, you can maximize QU. So, these are the attempts to reduce this QL, that is how we understood. Okay. So, operation wise it is something like it is double wall like concentrative tube Okay, so fluid flows inside the heat transfer fluid, and then in between this concentric tube there is evacuation. No, nothing is there. That's how you can reduce the heat transfer losses. Okay. And sometimes when we use this heat pipes technology, so I can deviate slightly more from here. So what happens if you see our electronic devices in laptops? You need cooling, right? So for cooling, what are the devices you use? Like chips are there, it cools. So heat pipes. So heat pipes are used in your machines, in your computers, right? So heat sinks are there. So you know how fast you can remove. Okay. Suppose if I have to gift a laptop to Donald Trump, then maybe I could have designed this laptop by using maybe platinum or maybe some gold, okay? Because it is having high thermal conductivity. Okay, it will reduce the heat transfer very quickly, and then he will be very happy. So when it is heated, when quickly it is dissipated to the air, right? So, but it is not possible for everything, right? Every people like gold may make all those plates where all thermal conductivities are there, like no heat transfer is there. So we need to compromise. So here again we cannot invest very high conductive material. So this is something like this is tube and vacuum is here, okay, and here it's a selective coating so that we can maximize the solar radiations. And what happens, there is a wicks, and this is evaporator and this is the condenser. Okay, so what happens, heat actually carries from here, your solar radiation is falling, heat generation will be more, and it will carry cold fluid in, hot fluid goes out, and then here heat actually heat transfer takes place, and you can take this heat for utilization, and QE will be here, and series of this kind of things are attached together, and fluid will flow, and you can get the energy out of the system. And now interesting thing will come. I think you will quick now. Okay, so solar radiation part. So see what is happening. This is a hot object, and this is a cold wall, and nothing is there inside. It's a vacuum. So what kind of heat transfer will be there? It's a radiation. So any object if you kept at a temperature more than absolute zero, it will emit thermal radiation, right? So that's what it is used. So body has to be more than absolute zero, okay, and bulk of thermal energy emitted by a body lies in the wavelength between 0.1 to 100 micron. That you must always remember. Thermal radiation, range is 0.1 to 100 micron. Okay, so solar radiation also falls in that range. So that energy transfer from the sun to the earth is by radiation. Okay. See, there are two principles. One is Maxwell's electromagnetic theory, and the second one is Max Planck's constant. Okay. So this Maxwell's electromagnetic theory, radiation is treated as electromagnetic wave, and for Max Planck's concept, this radiation is treated as photons or quanta of energy. Okay. But no such principle is there to explain the radiation spectrum very exhaustively. Okay, that you must know. Okay, and both the concepts are utilized to describe the emission and propagation of radiation. Okay, so result obtained from electromagnetic theory used to predict the radiation properties of the material. Okay, but the result obtained from Planck's concept have been employed to predict the magnitude of radiation energy emitted by a body at a given temperature. So that's how two things are different, but it gives the radiation spectrum of the system. Now this thermal radiation, as I said, its wavelength from 0.1 to 100 micron, and solar radiation is 0.1 to 3 microns. Okay, thermal radiation range is very high, right, and solar radiation range is very, very small. And what is the visible range? Because most of the solar PV systems works on visible range. So this is 0.4 to 0.7 micron. Okay, in that range only this solar cells will work best. Okay, and ultraviolet ray is 0.4 to 10 to the minus 2 micron, and infrared, actually we are interested more on this infrared because we are heat and thermal collectors, okay, at this moment. 0.7 to 1000 micron. Okay. And also you can see how big these radiations are, or say small. Okay. So for building size, humans, radio wave are very high, right? Then microwave, infrared, it's like honeybee, then pinpoint, then you can see like ultraviolet rays, and then the gamma rays. These are like atomic nuclei. Okay. And also you can see this application of those radiations. Gamma rays, it is less than 0.01, then X-rays, where it is used, right? Radiologists, people knows it, right? Ultraviolet rays, then visible range, it's the night vision, infrared, near infrared, then thermal images. You can see the applications, already you know majority of the applications. Okay. Okay, this angle is 32, and if you convert to degree, it will be 0.53 degree. Okay, and this is one astronomical unit, the distance between sun and earth. Okay, and you know winter solstice and summer solstice. Okay, what is the day? June 22 and then December 22. This is the summer solstice, where declination angle will be minus 23 for 23.45 December 22, and here is a plus 23.45. Okay, this is summer solstice, and for we can say winter equinox and summer equinox. Okay, in the winter equinox is 21, where declination is 0, and summer equinox in September 23, when delta is 0. So here we can say delta is minus 23.45 degree, and this is plus 23.45 degree, and this is 0 degree, and this is 0 degree, this delta. Okay. So for March and September 0, and then for December and June it is 23.45 in magnitude. Okay. So it always, and our angle, this attains an subtended angle of 23.5 degree always. This is known to you, right? It's not something like it is at 0 degree, it is rotating. So these informations are required. So solar constant. So if you are there above the Earth atmosphere, so our things are something like this. You have Earth atmosphere, okay, this may be Earth atmosphere, and what is happening here beyond the Earth atmosphere, what we call is extraterrestrial region, and inside this what we call is terrestrial region. Okay. So beyond this, what happens, that is not affected by any elements, or maybe what we can say, when solar radiation is coming through this Earth atmosphere, what we received is in attenuation form or attenuated form. Okay. That means solar radiations are attenuated by absorption and scattering. Okay. So how this will happen, I will explain soon, but beyond this it is extraterrestrial region, where ISC is 1367. Okay. But since n is varies, so this also varies. Normally this intensity of solar radiation in the extraterrestrial region is 1367 watt per meter square. Okay. But it varies because n is varies. So that is why this value is 1367, and extraterrestrial radiation is this, and this actually accounts for different things like its variation. Actual solar radiation flux is plus minus 3.3% variation, because sun earth is not at the uniform always. So that variation is about 3.3%, and that actually accounted here 0.003 cos. Okay. So that is how it is related. Okay. And that is how we can see for different times n is the nth day of the year, what is n. So and you can find out, you can substitute, and you can see what is I external, or what is called extraterrestrial region. So now I'll just explain the propagation of solar radiation. So for example, this is the Earth surface. Okay. So what happens, solar radiation comes and actually some are reflected back. Okay, some are actually comes directly to the Earth's surface. This is the upper layer of the Earth atmosphere, and this is the Earth's surface. Okay, so it comes something like this, and some are diffuse radiations. They don't have specific. These are anisotropic, right? There is no specific direction. So what my concern is, so this is Earth atmosphere. So Earth atmosphere composed of different layers. Maybe ozone is there. Okay, ozone layer already you know. Then you will have H2O will be the water vapor. Carbon dioxide will be there. Then methane will be there. Carbon monoxide will be there. Nitrogen will be there. Then we have dust or particulate matter, I can say PM. Okay. So what happens? You will have scattering will be there. Suppose this is a water vapor, so it will scatter. Is sun. So solar radiations are coming. It's electromagnetic radiation, right? It's a short wave radiation, electromagnetic radiation. So as soon as it comes to the Earth's surface, what happens? Some radiations are reflected back. It's irradiated to the space. Some are goes in. Some are goes straight way to the Earth's surface. These are called normal radiation, or I represent it as an IN. Is the normal radiation or direct radiation. And what happens? There are water molecules and then other gases. When solar radiations comes, it actually scatter. It actually is directionless. There is no proper direction, and its intensity decreases. What happens actually? One is absorption. ABS. Absorption happens. Other one is scattering. So this absorption happens because of O3 and H2O present in the Earth atmosphere, and scattering happens because of all the gas molecules. You just name it: carbon dioxide, carbon monoxide, nitrogen, then some kind of refrigerants gases, and maybe particulate matter. Because of this, what happens? You will have one more radiations called diffuse radiation, ID. One is for normal radiation or direct radiation, other one is diffuse radiation. Okay, the intensity of diffuse radiation is always lower, right? But contribution of diffuse is also important as far as solar energy conversion is there, right? Now, what technology to be suggested based on the radiation spectrum? That's the concern point. If your normal radiation is far higher, say for example, if you consider a place like Gujarat and Rajasthan, you will have more normal radiation. So in those places, it is very easy to install the solar concentrator as well. Solar PV will anyway work. Solar concentrator you can suggest. But a place like Shillong, so you will get mostly diffuse radiation in most of the cases. PV will work. Solar thermal will also work to some extent, not that very high, but there is a requirement of exhaustive study in those places to investigate the performance. Okay, you got this idea? So when solar radiations entered in the Earth atmosphere, this will be attenuated due to absorption and scattering. And absorption happens because of O3 and H2O present in the Earth atmosphere, and scattering happens for all the gas molecules presence and particulate matter. Okay, and we are defining two radiations: normal radiation or diffuse radiation, direct radiation, and then diffuse radiation, right? So you will get this kind of spectrum. So here is the dotted line is the extraterrestrial radiation. So extraterrestrial radiation will be something like this, and this part is your মই ফোন কৰি আছোঁ দেই, মই টকত আছোঁ। and this is for visible range, and this is UV, and this is the infrared part. Okay. When we consider that radiation study beyond the Earth atmosphere, we call it as extraterrestrial radiation, and there radiation are falling normally everywhere. Wherever you stand, you will get the normal radiation on your head. Okay. So that's how we can say it's a AM0. AM0, how do we define? So suppose this is the radiation travel in the Earth atmosphere, primarily we say something like that. So this, if we may consider, this is A, this is B, and this is C. Okay. So this AB by BC is equal to cos of theta z. So this cos theta, now this AM0 implies radiation is in the extraterrestrial region, but when sun ray is on your head in the terrestrial region, then AM is equal to 1. So if AM is 2, that means your angle is 60. Okay. So normally solar collectors are tested at an spectrum of AM 1.5, where this angle is 48.8 closely. So at that angle normally solar modules are tested. So that's why these spectrums are very, very important. So AM spectrum, they say, when you see the solar panels are coming out or solar modules are coming out, they actually tested at AM 1.5 always. Okay. That's how this AM air mass, it is AM stands for air mass spectrum 1.5. Okay. So you can see this like it's a radiation spectrum, and you can see this 44% of the energy is there in the visible ranges, and rest is in the near infrared and other wavelength, and UV is about 7%. Okay. So from here also you can conclude what could be the maximum conversion efficiency of a solar PV module, because 44% energy is there. So what could be the maximum efficiency? You cannot have 100% efficiency, right? So all the energy what you are getting is 44% energy of the entire spectrum. Okay. So here what I am showing, it's a sun is a black body, its black body temperature is 6000. So how can you say it's a black body? So we can actually test it. If you know the Planck's law, and then if you integrate this all wavelength from 0 to infinity, then you can find out the Stephen Boltzmann constant. Okay. So Stephen Boltzmann, you know EB is sigma t to the power of 4. Okay. So if you substitute the solar constant value, and if you try to find out temperature, that temperature is close to actually 6000 degrees Celsius or 6000 Kelvin. Okay. So then if you take that temperature and vary this wavelength, then you can get the similar spectrum. That's how we can consider it as a black body temperature. Okay. So hot sun radiates at shorter wavelength that carry more energy, and the fraction of absorbed by the color earth is then re-radiated at longer wavelength. So this is coming from the sun, and more amount of energy is carrying by the wavelength which is or radiation coming from the sun, and it is long wave is propagated from the earth surface. Okay. And that's how you can see the maximum wavelength is 10 micron in case of long wave radiation. How much time we have? Then if someone interested can also find out, like if I give this solar constant value and then radius of the sun and then mean sun earth distance and then sigma value, then we can find out like amount of energy emitted by the sun and then amount of energy received. Then this calculation will give you a temperature equivalent to black body temperature. Okay. We will also solve in the coming classes. Okay. So this is air mass things. Normally 1.5 spectrum is something like this, and this is the spectrum at which we work. Okay. So again we have some measuring instruments. So quickly I will just browse through. Suppose if you have measuring instrument, it is well and good. You can get all the data. If you don't have, then what you will do? if I ask you to do the measurement for or do the calculation for solar energy calculation, then if you don't have data, then what you will do? You will see a place of similar climatic condition and take the data from that place. If that is also does not exist, then what you will do? You will use some kind of correlations. Okay, so that will actually give you the radiation spectrum. That's how it is given. Okay, so it may be cloudless sky or maybe cloudy skies. Okay, and we have this kind of radiation you really expect in most of the cases, right? But you will have this kind of radiation. When cloud comes, it is very erratic and it's very difficult to predict, right? And if you consider a place, then always you will get this kind of things. Then how to design? That's a big thing. So if you know the characteristics, it's always good. If your radiation is something like this, it is very difficult to design. Okay. And these are instruments I was talking about, like heliometer, pyranometer, then we have sunshine recorder. So these are the instruments normally we use for solar radiation purposes. Okay. And these are sensors we use because we need to know the knowledge of thermal conductivity, and then what is called we have thermocouple functions. So if you have two dissimilar metals and you keep the two different temperatures, it will generate EMF. Okay. So that principle we apply. Then when we consider pyranometer, what happens when solar radiation is falling and then there is a black surface where we will place this kind of heat sensors, and then other sensor is at the beneath which is not affected by the radiation. Then EMF generated is actually converted to in terms of watt per meter square. So that's how we do the calculation. Okay. So radiation we measure this way, like Langley, he was famous scientist, and he first measured his spectral distribution, and that's how we know him. Like Langley is also a unit of solar radiation. There is one Langley is 1 calorie per centimeter square, which is equivalent to 1.163 into 10 to the power of -2 kilowatt hour per meter square. Okay. And you can see annual average solar radiation received in terms of Langleys, it's about 450 per day, and peak is about 600 Langleys, and in winter and monsoon it is about 300 to 400 Langleys. Okay. And you can see the radiation spectrum of India here. So red color means more, that is about 5.5 to 6 kilowatt hour per meter square. Okay. And in our place, even though it is not red, very popular, but it's fine, our things will work actually, it's not a problem. 4.5 or 5 if you get, then it will also work best. Now something to go again. We have how much time normally we have? Pushpender, then tutorial is there. Maybe 10 minutes I can take, and then we can start that. Yeah. So we have instantaneous and global flux, then hourly values. Sometimes what happens, even though radiation parameters or radiation informations are with us, actually these are not in a good form. Suppose your requirement is hourly, but the kind of data you have is the daily average data. So again you need to process it for your requirement. So that's how there is a need of studying those aspects like daily global and diffuse flux incident over the whole days, then what happens, and then hourly what happens. Okay. So we need to study in different dimensions, like in watt per meter square, joule per meter square, but mostly what we are interested about insolation, which will give you watt per meter square is the reading. Okay. Now we have beam flux and equivalent beam flux. Suppose if solar radiation is coming here, okay, it is IBN and it is at certain angle, say theta or theta z, it is any angle. So it is equivalent is IBN cos of theta z. Okay, that's how it is. So beam flux is IBN, and then IBN cos cos theta 2 is the equivalent wave flux. Okay. So, normally this theta is actually composed of many angles. Okay. So, this is zenith angle theta 2. So, this is radiation which is coming from the sun, it makes an angle of theta 2 with respect to the normal to the horizontal surface. Okay. And these are different angles which are related to this solar geometry. Okay. So, you have this globe and these are the observer's meridian, okay, and this is the what is called different slabs. What you can say, we can just to define this latitude and longitude, this is equator, and if you want to write this one, this is like your longitude, and already I defined latitude, right. Okay. This is already known. Yeah. So, declination already I defined, and it's like equinox and all. So, delta actually mathematically you can say 23.45 sine of 360 by 365 284 plus n. So, n is the nth day of the year, and once you know, say for example January 1 it will be n is equal to 1. So, February 1 it will be 31 plus 1 32. So, that way you can count these n values and you can find out delta. So, delta values varies from minus plus 23.45 to minus 23.45. So, 0 in where in equinox days, right, summer and winter, and other values you can see December and then June. Our angle, since it is 1 hour is 15 degree. Okay. That means, if we draw this, okay, and this omega is 0, okay, and this part it is positive from solar noon and is negative. What happens if we have to find out at 13 hours, this is actually 1 hour and this is 15 degree, and sorry, I will just cut it, otherwise it will be disturbing. It is minus 15 degree, okay, and if you have to find out at 11 o'clock, it will be plus 15 degree, okay. And if you are interested about 10:30, then what will happen? Half an hour is 7.5. So, that way you can find out this hour angle, and it varies from minus 180 to plus 180. Okay. Just I will take, say suppose if I consider a horizontal surface here, this is horizontal surface, and this is north, this is south, this is east, and this is west. Okay. So, sun is here, solar radiation is falling here, and this is normal to the horizontal surface, okay, and this angle is your zenith angle. Okay. And if we project on this line on the horizontal surface, and if we draw this, and this angle is your gamma s, and this is alpha s. This is altitude. This is altitude angle, and this is solar azimuth angle. This is solar azimuth angle. So, here sun is here, and this beam flux makes an angle theta z with the normal to the horizontal surface. Okay. And I am projecting on the horizontal surface, okay, towards due south. This angle is gamma s, and this angle is alpha s, and this is altitude angle, this is solar azimuth angle. Okay. Again I will draw here. to surface. Now I will define the surface azimuth angle. Okay. So this is important. Then I will just conclude few things I will discuss maybe other. So we will have, we will make something like this, and it makes an angle beta here. So one is perpendicular to the horizontal surface, other one is perpendicular to the normal surface, and this may be sun, and this will work something like this. So this is theta, theta and theta, these are different. This is theta and this is theta z, and this is normal to the inclined surface, because this is at certain beta, normal to the inclined surface. And this is normal to the horizontal surface. Okay. Already you know what is this. Okay. This is gamma s, and also you know this is alpha s, but this is gamma. This is surface azimuth angle. So what I have drawn here, this is the sun ray or beam flux, and it makes an angle theta with respect to the normal to the inclined surface, theta z with respect to the normal to the horizontal surface. Okay. So this theta z is always with normal to the horizontal surface. Okay. And then if you project on this horizontal plane, and what angle it makes is nothing but actually surface azimuth angle. Okay. Earlier what we have discussed is solar azimuth angle, right? And this alpha s is very important when we talk about beta values. Okay. And mostly this gamma is very important, and of course this is north, south, then east, and this is west. It's clear? All the things you will get actually in the slides. So slope is beta. I don't have to explain it now. Okay, it's a beta only, and already I have explained the geometry. So theta you will get is many angles. Okay, so origin you don't have to think much. So it will actually it will be expressed something like this. Okay, and based on the situations, this expression will be simplified to a very small expression. Okay. So I will just show some of the interesting thing, like what happens if it is vertical. Of course, beta will be 90 degree. So if you substitute the beta value 90 degree, then you can redo the calculation. You can see it is very simple expression. And if it is along the due south, then gamma will be 0. So your expression will be something like this. So different situations you can actually modify the expression and do the calculation. It's very easy, right? So maybe no, I will not extend further, because we need to solve some problem as well, and you need also break. Okay. So we can find out what could be this time, like length of the time, like what I mean to say, like sun, how long the sun will be there in a particular, and what is the maximum duration of sun's hour. So that can also be find out by doing this calculation. It is like TD is 2 by 15 cos inverse of minus 10 delta and 10 phi. Okay. So this can be calculated, and you can find out if you know phi and delta, then you can find out what is duration TD of the day length. Fine. And in solar calculations, we never consider standard time. We consider solar time or local apparent time. So this local apparent time is standard time plus minus 4 LST minus LOC plus E. What is this 4 and E? Actually, we need to have two corrections. And first is difference between the longitude of a location and a meridian on which the standard time is based, and this correction has a magnitude of 4 minutes. for every degree difference in longitude. And equation time is due to the fact that Earth's orbit and rate of rotations are subjected to small variations, and the difference in minutes between the solar time and standard time can be something like this. Okay, and while doing the calculations, you must sure that know which hemisphere you are doing the calculation. If you are in eastern hemisphere, then negative sign, and if it is western hemisphere, it is positive sign. Okay, and then you can find out the standard formula is there to find out this E, and E what you will get in minutes, and you can find out. Okay. So, and Cleans has recommended some this. Normally what happens when you need to find the radiation spectrum, you need to know what is happening in every day. Okay, but it's very, very tedious to calculate the radiation spectrum, what is happening every day. So what people have done, they have identified some representative days. For January 1 day, February 1 day, and if you do the radiation calculation on that particular day, that means you are done. So that will give you the radiation spectrum of particular month. Okay, so that's how it is represented. March it is, sorry, January it is on 17th, February 16th, and again March 16th, and you can see the dates to be considered to know the representative day for a particular month. So maybe I'll stop here because these things will calculate in the coming tutorial things. Okay, so thank you very much for your patience, and we'll continue now for doing some problem. Okay, so maybe I can give a 10 minutes break, then we will start. Thank you. they will just discuss those issues. But you use your things. So this is a tutorial session. In half an hour we need to complete this. So there are 3 problems I have kept for this session. Here overall loss coefficient for flat plate collector with 2 glass cover we have considered. 2 glass cover is there and 1 absorber plate, and dimension is given, and spacing between the first glass cover is 5 centimeter, and maybe I'll draw somewhere. So it's something like this: glass cover 1, then glass cover 2, and then we'll have absorber plate, and the dimension is given, and spacing between the first and glass cover is 5 centimeter, and both the cases it is 5 centimeter. This and this, it is 5 centimeter each. And emissivity of the plate is given. This is plate is it 0.9, and these 2 cases it is same, it is 0.85. Okay. And its tilt is 23, this is 23 degree, this is beta, okay. And ambient temperature is given as 25, wind speed is given, and back insulation thickness is 10 centimeter, and side insulation thickness is 5 centimeter, okay. Insulation thickness is given, thermal conductivity of the insulation is given, and we can use different correlations for calculation of heat transfer coefficient. Okay. So already you know the expression. So QL or maybe QT. Okay. So this QT by AP need to be calculated. Radiation from the absorber plate to the glass cover 1, glass cover 1 to the glass cover 2, and then glass cover to the T sky for radiation, and T ambient for the convective transfer, right. So, and these properties are given to you. So, you need to find out the properties. I will just explain the way you need to solve it. I thought of solving it, but I think we don't have much time. I have solved it for you. It's not so. Just a minute. Okay. So, see all the informations are given. TPM is 73, which is given. Okay. This is 73 plus 273.15, it is 346.15 Kelvin. Then ambient is given, we are converting to Kelvin. Then the sky temperature we can calculate, because T ambient is known, TA minus 6 is T sky temperature. Now, if you see here, what you need to find, TC1 anyway not given to us, and TC2 is not given to us, and other informations we know. Okay. TPM is known, and HPC1, this is also not known. This means what? This is plate, this plate to C1, that is why it is HPC1. Then C1 to C2, this is C1 to C2, and then C2 to T sky. Okay. Actually, this is ambient, this is not T sky, and this is T sky. So now, what assumption we make in the while discussing this phenomenon for heat transfer from the observer plate to the ambient, what we have discussed, this T PM is greater than TC1, is then TC1 is greater than TC2, and TC2 is greater than TA or T sky, right. So that strategy you should keep in mind. So already you know TPM is 346.15. So these two temperatures TC1 and TC2 is unknown. We need to assume. At the same time, you know what is TA, and T sky can be calculated. T sky is 292.15. So your range of consideration is in between 346 and 292. So in between you need to assume the values. So what assumption you can make? Okay. So either you can make something like this, TC1 is 328 or TC2 is 306, or maybe you can do it, you can do something else. So if it is closer to your assumption, then you don't have to do so many trial and error, but if it is very far, then you need to do it. But your assumption should not be something like TC1 cannot be more than 346. So if you are doing, that means 350, so you are doing wrong, your understanding is wrong, and you cannot achieve this what is called your conversation or convergence. So that's how we have considered TC1 328 and 306 here. So this is not hard and fast, this temperature only you need to consider, but you must know the range of consideration, right. So once you know this, then these things are known, okay. Then this temperature is already 346, and you have assumed this TC2, TC1 is 328. So as I said, if you have to take the properties of air, then what you need to do? You need to take an average temperature between these two. So take the average temperature, and then that average temperature you find out the properties of the air. Okay. So that's how this T mean is 346 plus 328 by 2, and then what you will get, it is about 337.07 or 63.925 degrees Celsius. So at this temperature you need to find out the properties. Okay. So how to find out the properties here? So what's the temperature? 63. So 63, this is in degrees Celsius. So 63 is not here directly. So this is 60 and 70. So you need to interpolate. Okay. So interpolate, then you need to see what are the properties you need. Thermal conductivity is always required. So it is increasing. Okay. So you know how to do interpolation. So say for example, I'll just show you once because this is somewhat fundamental. Say 60, I am interested to find out what is thermal conductivity, and it is increasing, right. So K at 63, just for your information, is, say for example, thermal conductivity 0.02808, okay, this plus 0.02881 minus 0.02808, right, divided by 10, right. Then what is the difference is 63 minus 60 is 3, right. So once you do, then what you will get at what is the conductivity at 63. Okay. So accordingly we need to find the values of nu and Prandtl number for that. Okay. Now next is, once you know this parameter, then what is your next calculation? You need to find Rayleigh number, Ra cos beta. Beta is also known, beta is 23, and Ra is Rayleigh's number. So what is Ra? Is multiplication of Prandtl number and Grashof number. So, what is the Grashof number? Prandtl number, this beta is different, it is 1 by T. So, this is 1 by T actually. So, I will not write beta, 1 by T, and this T is T mean actually, T mean, beta z, then you have delta T, L cube, then you have nu square. Okay. So, you need a properties, and this is L is the this is characteristics length between these two plates. So, this length, and delta T is the temperature difference between these two glass, and Z is acceleration due to gravity, and you can, and this T is T mean, you can find out what is Ra, and once you know Ra, you can find out Ra cos beta. So, once you are confirmed with the values of Ra cos beta, then you can find out what appropriate correlation you need to be used. So, once you know some values of Ra cos beta, then you know what correlation to be used. Okay. So, then you need to find out what is the best thing for correlations. So, Ra cos beta you got this. So, accordingly you need to use this expression. Okay. And then since you are interested for plate 2 glass cover 1, then H PC1 into L by K, then you express it and you just find out the values of HPC1, and this is the heat transfer coefficient from plate to the glass cover 1. Okay. Then you find this C1, again C1 glass cover 1 to the glass cover 2. Okay. So, for that again you need to find out the temperature, because temperatures are different, TC1 TC1 and TC2 are different, then mean temperature will be different. So, mean temperature will be different means your properties will be different. So, you need to find out the properties, and then you find out Ra cos beta. Okay. And then what you will get is the value of Ra cos beta, and you check which correlation to be used, and this is the correlation you can use, and you can calculate HC1 minus C2. Got it? And also then from glass cover 2 to ambient. Okay. So, other expressions what you have, these expressions is done, HW TC2 minus, this is not actually sky TA, and this is sky. Okay. So, this can be calculated already, we know some of the correlations for finding out the HW. Okay. So, you can substitute these values and we can find out this HW. Then we check the values of all QT by AP for this expression, for this expression, for this expression. If it is similar or identical, then you are done, you are safe. If it is different, then you have to consider a fresh assumption and do the same calculation and see at what condition you will get the similar values of QT by AP. Okay. Then you take the average and then you find out what is the UL. Okay. So, this equation 1, 2, 3 has to give the same values, and once you are done with this, then what you can find out is average of these things, maybe this plus this divided by 3, that will give you something like QT by AP, and of course, this has to be very, very close. This is close values, close or say close values. Okay. So, already you know this is something like UT and this is delta T, right. So, once you know this, then you can find out what is UT. Delta T is known. So, UT can be calculated. So, other values like UB, which is very, very easy to find out, just you use the expression, and US, and then sum it UB plus US plus UT. Okay. This is UL. So, if this value is less than or in between 2 to 10 watt meter Kelvin, okay, sorry, meter square Kelvin, then your design is perfect. You got it, right? But concern is your assumption. Your assumption is, if your assumption is no valid or no justifiable, then you will get the no convergence early. Otherwise, you need to do many a times. Got it? So, this is one interesting problem, and it gives you an idea how to know reduce the losses and how to optimize the collector efficiency. Okay. So, here you can see already this is done, what value we got. So, QT we have again no varied because values are different, and then we got a appropriate value after doing a lot of iteration. And then we have calculated UT, and UT is found to be 3.664, and UBO we got Ki by delta B, because Ki is thermal conductivity of the insulation and delta is thickness of the insulation. And side loss, we know the expression because these dimensions are given, length and breadth of the collector, and this is height and the conductivity and then thickness, and you can find out what is US, right. And finally, our value is found to be 4.8225, which is within the prescribed limit. So, our design is safe. Okay. So, this is a very interesting problem. Then also we can discuss this kind of problem. So, it may be calculate the monthly average of hourly radiation falling on a flat plate collector and having gamma is equal to 0 and a slope of 26 degree given the following data. So, New Delhi data is here and then time is given, and this is local apparent time. So, from here we can find out it is 12 to 11 to 12. So, 11:30 you can find out. So, 11:30 means plus 7.5 degree, omega is plus 7.5 degree, okay, because it is towards forenoon and it is time duration, if it is given, it is mid of the time we normally consider. So, in order to solve this, I will just go back what we have unfinished. So, here like why we have considered this, because this is Angstrom's expression and this relates global radiation to the extraterrestrial radiation and then sunshine hour and maximum sunshine hour, okay, and these are fitting coefficient. Okay. That means, if you know these radiation parameters and then meteorological parameters, you can relate this kind of correlation and you can find out what is the global radiation falling on a particular place. And this H naught bar, it is actually you cannot go to the extraterrestrial region and do the calculation, right. So, normally this is something like your sky without cloud, that means it is clear sky. Okay. So, clear skies resemble like you are doing the experiments in the extraterrestrial region. That is why we are more concerned about theoretical calculations, and that is how we did this the procedure by which we can calculate theoretically this H naught values. Okay. But this is actually on clear skies, since it is very difficult to measure. So, we made we should depend on mathematical calculations and that is how we can come up with this expression like H naught is something like this, and if we consider on a representative day, this H naught become H naught bar. So, now our representation is something like we say Ig and sometimes Ig bar. So, Ig bar is nothing but average, hourly average values we represent at Ig bar, and daily, so monthly average of daily solar radiation, then what we said capital H G bar. Okay. So, that is how it is H naught bar, it is the extraterrestrial radiation on daily basis, it is average of daily radiation, okay, or monthly average of solar radiation. So, that is how we can measure this H naught bar. Okay. So these correlations are used for different conditions. It may be for diffuse or it may be for beam radiation. So different correlations. I am not going to discuss all those correlations. But what is more important, this RB, because we have discussed this RB value, which is still factor, and for beam radiation, diffuse radiation and reflected radiation. For beam radiation, it is defined as the ratio of beam radiation flux falling on the tilted surface to that falling on the horizontal surface, and that is how it is sin delta, sin phi minus beta. Delta is declination and phi is latitude and beta is tilt, and this is our angle omega. So that is how it is related. And for diffuse radiation, this tilt factor is something like 1 plus cos beta by 2. Each is actually represents the shape factor, a radiation shape factor with respect to the sky. And for this reflected radiation, 1 minus cos beta by 2, here is 1 plus cos beta by 2, and this 1 minus cos beta by 2, actually this is nothing but radiation shape factor with respect to the ground, and this is like reflectivity of the ground, or it may be concrete surface or maybe grass surface, and its value is about 0.2 for grass surface. Okay, that is how we can measure RR, and then total radiation flux is something like this. That is IB-RB plus ID-RD plus rho RR IB plus ID. So that is how we measure, and we can also simplify if we are really interested for daily radiation. So daily means in hourly we need to integrate over the entire day. Integration means omega only the variable here, because time will vary from sunrise to sunset. So if we introduce this, and this omega will come at the front in both the expression. So only difference is omega if you compare to this daily in hourly. Okay. So these expressions are need to be used for doing this calculation. Now what we are referring. Okay. So now I will again go back to this. Yeah. So I will just explain the procedure how we will do it. First, what you need to do here, we need to find out delta. Okay, gamma is there. That means your things are very, very simple now. So it is due south, is in due south. Normally solar devices are installed towards due south, because you will get the maximum exposure to the sun. Okay. So gamma is 0 under that condition. Okay. And here see what is phi here, can someone tell me? It is 28 degree plus 23 by 60. So this is as a whole degree, right? So this is phi, and then you will have omega is 7.5 degree, because this is time in between 11 to 11:30. So I am considering 11:30 is the time. Then what else? Delta you need is 23.45 sine of 360 by 365 284 plus n. Okay, n is the nth day of the year. So what is n here in October? In October, what was the day? We consider it's a cleanse recommendation, or one day gives the gives the entire information of the particular month, right? So anyway, maybe you consider 15th. Sometimes if I ask questions, I consider that you don't need to remember. You consider 15th of the day is fine. So say for example, I consider 15th of the October month. Then January is 31, February, then March, April, May, June, July, August, September, then you will have 15. বানাইছে। ঠিক আছে। So what's the value of n here? You can find out the n values. Okay, n values you can find out. So once you substitute there in n, then you can find out what is delta. Okay, so what is known here? Phi is known, omega is known, then delta is known. Okay, then this information is fine. You can actually know use those expressions. You can find out what is ID values. So if I now share the other expression, then you can see so here you can find out all those values RB, RD and RR, then these informations are given. So from here you can find out what is IT, because these are all are known. Beta is known, so RD is known, 1 plus cos beta by 2, then RR is rho multiplied by 1 minus cos beta by 2, rho is 0.2, okay, and beta is known, so these values are known. Okay, so you can very easily find out what is IT, right. So this is very important informations, like if you know these angles, okay, because these are the angles you need to know, and omega is also known, then how to find out this total radiation, hourly total radiations you are receiving in a particular position. Okay, so this is another example. You can actually do exercise in your hostel today, and these all are related to design, right. And third problem is like we have collector tilt. Already I said what happens if you consider different beta values for different climatic conditions, then you will get different values of performance, right. So in this case, if you consider this problem, so these are the radiations measured for the place, latitude longitude is given, and we need to calculate the maximum tilt of a flat plate collector for 3 different situations. First thing is insolation falling on the array over the whole year is to be maximized. So I am not going to change the beta value every time, only one beta you will consider for entire year. Second thing, insolation for the month of December, January and February. For the winter months we are going to fix, because I need the hot air. Okay, and third is insolation for the month of April, May, June, because I need some to meet for drying purposes. Okay, so 3 different conditions I have placed, and then how we can do it, and what information is given, like HB is given, radiation weight is falling. So these radiations and then n values are known based on the representative day. Okay, so now how to calculate this beta. Okay, so this is quite interesting. So I have already done it. Please do it. I will share this, and you please do it. So I have done this calculation. So, n values and delta phi minus delta, then HB10 phi minus beta, and we know how to find out this beta optimum for different conditions. Okay. So, if you substitute, interestingly if you see for the first case you will get a beta value of about 12.01, and second case you will get 16.97, and third case you will get 4.4. There is a huge difference, right? 4.4 and 16.97 is really difference. So, its impact is really significant. Okay. So, it is not something like only one beta you give and then it will work throughout the year, but based on your requirement you can set beta values and you can perform the or you can design the system for better performance. Okay. So, if you do in your own, then you will realize more, okay, this is how we can do the calculations. Okay. And it is really interesting when you do and then you realize like importance of this kind of numericals. So, I thought this problem you will solve and I will help you solving. Maybe next time I will do it. Okay. But this is because of shortage of time. So, I think we are done for this session. So, thank you for your presence, and we are meeting sharp at 3 o'clock to listen a very nice talk from the professor. Okay. Thank you very much. So, you can have your lunch and come back by 2:45 here. Okay. Thank you.
Thank you to everybody to be there. So there is many slides, many on PV fundamentals. So sometimes I will say if you are interested on this topic, you can read because it's more theoretical how it's operate and things like this, and focus on more important thing. Okay. And don't hesitate if you have questioning when I'm speaking. I can answer. So first, I will present where I am from. I am from here. So you have the map of France. Here it is the Alpine space. Okay. There is Italy. There is Switzerland. So we are not far from Switzerland and very close from Italy. We are just to cross a tube to go into Torino, Italy. I am in the National Institute of Solar Energy, INES, and which is one of the 4-point spot in France where we are dealing with renewable energy. So in Paris there is the Institut Photovoltaic Île-de-France where they are dealing with mainly on new PV cells. In Pau, they are dealing with all kind of renewable energy. So gas, because there was gas resource in the past, and now they are working on biogas and hydraulics and things like this. And Promes, I will speak tomorrow about Promes, where there is a very specialized on high concentration, high solar concentration, and whereas in my institute we are more dealing with integration of solar energy everywhere. So integration in buildings, from building to cities. There is also some study to integration in vehicles, in balloon for atmosphere, for space, to be autonomous. In this area, there is one graduate school, so for training from master to doctoral study, and this one of Institute of Technology for Environment, which is led by the CEA. So at INES we are sharing the space between the CEA, Commissariat Énergie Atomique, Université Savoie Mont-Blanc, and CNRS. And so my lab is in this building, which is called Helios building. As you can see, it is in the Alpine space, so there is mountain everywhere in the surrounding. Here there is a lake in front of the campus. And all of these are testing facility of the National Institute of Solar Energy. So going from control condition to full scale, almost full scales and real condition. The graduate school is a part of, our university is a part of European Alliance of University. Europe decided to create some European university. We are implied in UNITA University, that is with joint university with Italy, Spain, Portugal, Romania, speaking that Romanian language. And we have several agreement and MOU, and I would like to have a MOU with IIT, Guwahati, with UNSW, with Singapore, NTU, with of course close universities, Saragosse, Torino, Genève, Hong Kong CTU also, and we have international running project for PhD. We have at that time a co-fund with Australia, and also national French and Singaporean research project with NTU. So the graduate school is organized between one training path for master student. One is dedicated to solar energy in terms of engineering, so it's called Energy for Solar Building and Cities, and one is about economic and business and law, because there is a lot of barrier in terms of the development of solar energy, in terms of insurance, in terms of business, and in terms of law. Who has the right to sell electricity, how you can sell it, how you can buy it, and market. There's a lot of issue. And one scientific poll, which is organized in 3 main topics with joint laboratory, my lab, LOCI, and LEPME is for solar resource at multi-scale needs. So LEPME is working on solar cells, and we are working on the integration of solar components. There is one scientific topic about solar resource digitalization for better reliability. So it's about all detection of fault, prediction tools, as I mentioned this morning, with 2 labs. One in applied mathematics, one in informatics and data treatment. And the third topic is around how to diffuse, to help the diffusion of solar energy. Is mainly done by a lab on economics and business, and one on law and insurance. So I will start to deal with integration of PV in buildings. So first I start from the physical process of the photoconversion, and then how we characterize this performance, the performance of the module. What are the issues regarding the integration of these modules? And what is the main? What are the main components of a PV system? What do you need if you want to install a PV system connected to the grid or off-grid? So as it has been shown this morning by Professor Kalita, there is 2 ways to produce electricity. First is thermal. If you can reach higher level of temperature, you can produce some steam, and then from steam generate electricity. Second is direct photovoltaic effect, where you are using solar cells. We will see in the next day also the different type of components for solar thermal, low temperature, low and medium, that we could use also for cooling with solar thermal, or for electricity. So finally, with solar technology, we are able to try to answer to building needs. And we have to know that a building and a city are the biggest consumer in terms of energy, so it's interesting to see some combination. It has been presented this morning some data about solar thermal. Here I'm presenting about solar PV. So it is extracted from the International Energy Agency, that said that it will be the solar PV, the largest renewable energy resource in 2029. There is a big rush in terms of development of this technology. As you can see here, solar PV is now over the wind, is over the hydropower. Sorry. At that time, what is the market where there is a more big installation? Since a long time, until 2000, it was Japan the number 1 in terms of PV. Then it was Germany, and now it has completely changed. There is a big rush about China. At that time, 80% of the modules are built in China. They have a big industry to produce, and thanks to the COVID crisis, they develop a lot integration of PV in their own country, because they couldn't sell during a period, they couldn't sell abroad. So they decide to integrate massively PV. So at the time is at China, Europe, which is number 2. It's quite simple. Of course, Europe have a green policy, high level of interest for environment, but it has also to notice that in Europe there is no conventional resource. Okay, there is some coal, but not too much in Poland. But there is no petrol, no gas, except in maybe in the surrounding of Norway. So the conventional carbonate resources are almost inexistent, and since there is international instability, the price of this resource, conventional resource, can increase. Since the war between Russia and Ukraine, for example, there is no more gas coming from Russia. It was a big problem. So Europe is pushing a lot for energy sovereignty. So to be try to push a lot renewable energy to be as much as and possible independent from classical resource. And then you have US, as you can see. But you can see that India, India, no, it's not on this one, it's the next one, has a big push in terms of integration and development of PV, and there is a strong increase. At the time, this year, the more big implementation was Spain, Greece, Chile, Netherlands. So all countries that want to be independent of classical resources. And so, yes, it is here that we see that India has a strong increase in terms of implementation of PV. There is still China, which is pushing a lot for the development of big PV central, and then European Union, of course, a lot of money to put on the development in every country of PV. It's quite balanced between BIPV, so integration in buildings as a rooftop, even now in facade, and utilities, so it could be big PV central or other kind of application. But BIPV is so a very important market when we see this. So there is several applications of PV. The first was for space at the beginning. I will show you a short history. Autonomous apparatus like in the sea for security. We will see Friday, I think, solar PV pump and many different other. For BIPV, there's a lot of innovation of different shape, different color. We have work on printing also on PV to try to mimic some stone, some wood. So there is a aesthetical effort to integrate. So in terms of history, the photovoltaic effect has been highlighted in 1839 by Becquerel. Then there was the first solar cell with efficiency of 1%, very low. Albert Einstein then has a Nobel Prize about the photoelectric effect explanation. Bell Laboratory introduced first crystalline silicon, and since that time, crystalline is still 80% of the PV cells that are manufactured at that time. At the time, the efficiency was 4%. Now we can reach 25% for monocrystalline cell. Then there was first amorphous silicon, so it's film, what we call second generation of solar cell. Then Gretzel and so on and so on, and keep on. Now there is perovskite or new PV. So here is the history. It started by space. It was very expensive at the time. Then it has been developed off-grid. And then around 2000, it had a big rush in terms of development of PV, and especially for BIPV. And now there is PV central in the desert and things like this. Look at the manufacture; it's very interesting. I like to show at what time, who was the manufacturer, and I will explain later why. For off-grid, it was BP Solar, Shell, Total, all the petroleum company. The reason why is that they were going in some country to take some petrol and gas, and in exchange to integrate some facilities on so solar pumping, for example, has been developed also by this company for the village, to give water and things like this. So it was a kind of green window for this company that made interesting thing, developed interesting thing, but were extracting the resource. Then they disappear. I will show you why they disappear, this manufacturer. And for the big rush of the PV, it is the electronic company that decide to manufacture their own PV. So it was, for example, Sanyo, Sony, Sharp that decided to manufacture their own PV. And so this kind of manufacturer disappeared because there was a high concurrence for this. And now there is different still Sanyo, Sharp and so on, but there is a Voltec Solar, QCell, Sun Power, Longi that decided to create their own activity. This is from petrol, this is from electronics, this is fully dedicated to PV. So, and I will explain why this and why they disappear and so on. For space, so the first for space was for satellite. It was in 1958, the first American artificial satellite. Then in 1962, Tesla with just a power of 14 watts, and so on. And now the International Space Station is equipped with 110 kilowatt photovoltaic system, which represents 2,500 square meters. Very efficient modules, and sometimes they replace some. The astronauts are replacing some. Off-grid. So the first was for lighthouse, okay, for autonomous lighthouse. Then for broadcast program in Niger. So, for example, as I told you, is typically to give a good image of such company that was exploiting the petrol, and to give back PV, electricity, and so on. Of course, for autonomous area in alpine space, now some boats also use PV off-grid. On-grid, so it was in US for the first time in 1973, first house, and several after. In France, it's only in 1992. I knew very well the man that has integrated on his house this, because it was illegal. He decided to say, okay, in US they are putting PV, inject on the grid, and in France, you know, there is a big company called EDF, Electricité de France, who was fighting to no, we are selling our own electricity, we don't need more electricity. So it was forbidden by the law. And he decided to invert his counter and to put PV and inject on the grid, and it was a big polemic at that time, almost going in jail and so on and on. And since this, they start to integrate that in the law, but very late. And I know the man is very passionate about solar and still the same since that time. So it's near Lyon. And then in Germany, so several, and now there is bigger and bigger things. Mobile. It's funny to say that there was the electrical car already in 1962. We was integrating a PV cell on the roof, and so there was electrical boat, solar airplane, solar calculators, and so on. So different applications. Okay, so for this part I will not go deeply on the physical phenomena. If you want to read, it's interesting. The main principle is that you have silicium, okay, which is what we call doped in one side by Bohr thin film, which is doped P positive, and in the other side by phosphor, which is doped negative. This allows to naturally silicon when they receive photon, usually there is an electron of the atom which if he is receiving some energy, will try to disconnect to the atom. This is the principle. It is what he will cross what we call valence band, and thanks to the doping of this silicon, it will induce in one side more positive charge, in other side hole, also hole, so deficit in charge, and so if this component receive photon, it will help more the electron to change of valence band and to circulate from the P to the N. Okay, and at the junction, we try to collect this electron. Okay, if we collect electron, then we make a current. Okay, so it's the principle. So if we provide more energy than what we call forbidden gap, it allows the electron to change and to move, to migrate in the conduction band and to be collected by a grid which is at the surface of the material, so by micro wire. Okay, so it's the main principle. The atoms are excited by photon. As the silicon is doped in one side positively, in other side negatively, thanks to Bohr and phosphor, it allows to favorize, to enhance this process of transfer of electron. And the principle is to collect this electron to generate a current. Okay. So you can. In reality, with semiconductor, the energy which is useful is around wavelengths. Not all the spectrum, as this morning for the thermal, is useful. Only one part is useful. That means that regarding the spectral solar spectrum, there is a big waste in terms of collect, because one small part, around 20%, is collected and converted in electricity. The other part is heat, okay, which is not useful for PV conversion. It is not useful, but it could be a problem. If there is too much heat, the PV conversion is not good. That the efficiency will decrease. Okay, so 80% of the light is converted into heat, okay, and 10% could be reflected, and 10% converted, or it depends, more or less, now we can expect to have 20% in the module in terms of efficiency. So different technology appear. So arsenic de gallium, GAS, silicon, cadmium tellurium. Cadmium tellurium at that time is used for space application. It's very expensive, efficient also. Still the silicon, which is very used, well used, and because the principal resource is quite abundant on Earth. Amorphous silicon also is interesting, but so for silicon is around band gap is around 1.2 electronic voltage. So 1.2 EV is 10 power minus 19 joule. So it's very small amount of energy. Okay. So regarding the incident energy, some is lost because the energy provided by the photon is not enough for the electron to change. So it will generate internal heating. Okay, the electrons start to change and don't change, so come back, and there is photoconversion at the junction. There is also recombination between, so there are many physical phenomena inside the PV cells that more or less generate heat also. Okay, they are heat because the sun is heating the panels, but inside the PV cells there is also some phenomena that generate heat. So, and also there is a loss due to what we call parasite resistant. For example, if the surface is not perfect, if you have micro crack in the cells, or you can have a loss by Joule effect. Okay, all more or less is by heat, the loss. Okay, finally we model a PV cell like a diode. So it's going, the current is going just in one side, in one direction, from P to N. Okay, it's impossible to go in the reverse side. There is a resistance, parasite resistance that generate loss by Joule effect. And there is a shunt resistance which is linked to the normal resistance, electrical resistance of the PV module. Okay. For a cell, the voltage of the born of the cell is around 0.5 volts. The intensity that can circulate inside is around 20 milliampere per square centimeter. Very important data that are provided by us for a cell or for PV panels is this curve. We will see how we obtain that. Where you have, here you can see it is a maximum power, the product by intensity and the tension. The current and the tension is the power of the cell. It could be the same for modules. And so you see that there is a point which is a maximum power. The product of tension by intensity is maximum. So we call this peak power, okay, for a cell or for a module. This data is open circuit tension. So when your module is not connected, okay, and you measure the tension at the board of this module, you will measure open circuit, okay? When you have your module and you connect the two plus and negative, okay, it's a short circuit, and you will measure this intensity, short circuit intensity, okay? So all manufacturers should provide that, and it is provided at 1000 watts per square meter, and at 25 degree. Okay. And the efficiency is the maximum power by the product of short circuit intensity and VOC. Okay, the voltage is depending of the temperature, and it is this reason why I started to work on this field. Because originally I'm not from electrical engineering, I'm from thermal. But since the beginning of the 2000, I told you that it was the first massive integration in building. And people that were designing PV for building, after 1 or 2 years, say, I don't know, this PV central didn't produce what I was expecting. But I'm an expert on PV and I don't know. And the reason is that the temperature. Okay? The temperature level when you are integrating in buildings is higher than when you are not integrating in buildings. And generate a lot of issue. Now we clearly identify that it generates also aging of PV panels and so on. So voltage is depending of temperature and intensity, of course, about radiation. Radiation is important also to generate electricity. So temperature in one side and electricity. So here you have some curve depending of different level of irradiation. Okay, you will see. For different level of irradiation, the intensity will change. Whereas for different level of temperature, the voltage will change. Okay, of course, the power will increase or decrease. Okay, so the power will decrease regarding the temperature. And it is the first attempt to find solution to decrease this temperature, to the idea of hybrid photovoltaic thermal, how to recover a part of thermal energy and to maintain the operating condition for PV panels. We will see that it's not so simple, because if you want to have heat, you want to have to increase the temperature, and sometimes it's not good for the PV function. So we have to find a compromise. Okay, it's clear for everybody. So an important thing that voltage is depending of temperature and intensity of radiation. Okay. So the method to test in normal operating conditions. So normal operating condition is 1000 watt per square meter, 25 degree. Okay. So it's a flash generator. Here it's better to see. It's a big one. You see the flash test is at Ines here. You put the PV panels here, because now PV panels could be very big, part of big windows or facade. And here you have the flash test. So when you are flashing, the system will provide this. So the intensity V curve, okay, and the power. Okay. So you can easily find with the power, which is tension at maximum, intensity at maximum, and the open circuit tension and the short circuit intensity. Okay, so it's easy now also to recognize a classical IV curve. You have 4 parameters: short circuit, open circuit, tension maximum, intensity at maximum, and of course at the result. You can add some filter on such apparatus, because it's a flash, so you can add some filter that allow to displays the solar spectrum in one range of will filter such a range of wavelengths, decrease the global irradiation. Okay, you can play with that. I forgot we spoke this morning with atmosphere mass. So the standard for PV is to see that if the sun will cross the equivalent of 1.5 the width of the atmosphere. Okay. If the sun is perpendicular to the point, he is crossing 1 atmosphere. If he's not perpendicular, he's crossing, he could reach 2 atmosphere, okay, on the pole, for example. So for PV, the standard of the solar spectrum is 1000 watt per square meter, as if the sun was crossing the equivalent of 1.5 the width of atmosphere, okay? So AM 1.5. So here is some documents if you want to go deeper on PV. So the classical technology are crystalline. So you can see here. Here we can see that it is polycrystalline. You can see different way to reflect the light. Okay. Here is monocrystalline. There is no different aspect, and I will explain you how it is manufactured. Typically, one module has 34, 36 cells that are in series, so all connected. Okay. But now you have a lot of different ways. You can have 2 parallel series of. It's like a fractal system. Finally, what you find at the scale of a combination between cells, so parallel series, it's the same at the scale of a PV central. You can do the same. Okay. So different technologies. The more common are monocrystalline, polycrystalline, and as I told you, there is now a lot of different technologies. The more studied at that time are perovskite, but perovskite are full of expectation. At that time, the lifetime of perovskite is very low. It whereas this technology are still operating after 30 years. 35 years. Operating is not a problem. It's the efficiency that they have, which could be a problem, okay? Usually, the manufacturer gives some warranty. And the usual warranty they provide is after 25 years, okay, of operating, your module will have 80% of the original efficiency. Okay, you start at T0. After 20 or 25 years, the manufacturer will say, guarantee that the efficiency will be 80% at the origin. So it's not so bad. Okay. So there is we are speaking about generation of PV cells, and so of course is to increase the efficiency and to reduce the cost. At that time, the cost is very low because there is a lot of resource, a lot of PV panels on the market. As I told you, Chinese manufacture a lot of PV panels, and they were stopped during COVID time. They couldn't export anymore, and they were keep on manufacturing PV, and so. After, when the market opened again, the price decreased because you can find everywhere some PV panels at low cost, and it is still the case. Okay. Okay, what's this? So, polycrystalline, monocrystalline. Now the efficiency are keep on increasing. For monocrystalline is more to around 23 to 24 of efficiency, and for multicrystalline is a bit less. So the difference between mono and multi is related to the manufacturing process of the PV cells, and I will explain you how it's manufactured. Amorphous silicon, you can maybe have seen that it's a non-rigid substrate, so it's convenient. You could put on a tent or you could use for camping, but the efficiency is a bit lower. The advantage is that they are less dependent to the temperature than crystalline silicon. Okay, and the other technology, but we don't find too much. Thus, there was an attempt of using that copper and indium. It has not been so developed. The advantage of this kind of technology, they accept more diffuse. The useful band of wavelengths is bigger. So it's not like solar thermal, but it's better than monocrystalline. They can use a larger band of wavelengths. So it was tested on Windows, for example, because on Windows there's a lot of diffuse radiation and different radiation. But finally it has not been so much developed for building application. You can find here some. Okay, you have some kind of ink or perovskite. It is like this. So it's a kind of ink that you put inside a polymer cover. And the main problem is that if this cover is aging, which is the case for a polymer, usually a polymer don't like too much UV. At one stage, if there is a failure, contact with humidity or the cell is destroyed. Okay. So, but there's still big rush on perovskite cells, and the lifetime is still a problem for this. So you have many technology, many record, many ROS for the record, and you can see there are also some crystalline with multi-layers in order, we call that multi-junction, in order to use more wavelengths. So you can increase, now the best cells are more than 40% of conversion. But the price is, of course, expensive also, because they are working how to trap the solar radiation at the surface. So there is nanostructuration of the cells in order to trap the maximum of sun, and then multi-layer treatment for multi-junction. But keep on, it's a big area. So how it's manufactured? So it is coming from sand, okay? And just to give you some idea, for electronics, the purity has to be 99% of purity. For example, the processor of your computer, this quality is the same. It is a wafer, silicon wafer. But this is the purity. Whereas for PV, the purity has to be less, okay, less important. And the explanation, so you remember about the first manufacturer of PV cells. It was Total's, Shell, BP Solar. The electronic industry at the beginning didn't care about PV. And all the waste coming from the industry of electronic was almost given to the industry of PV. Okay, it was waste, not useful anymore for semiconductor and electronics. So the company like BP Solar, Total were buying it for low cost and manufacture the PV cells. When there was an explosion of the PV development, the electronic company say, wow, why shouldn't use also our waste to produce PV? So they decide to keep on making electronic components and so on, but use the waste of their wafer to produce their own PV. That's why the original manufacturer disappeared, because they have no resource anymore. Okay, so that's why Sanyo, Sony, Sharp started to sell, and Total, BP Solar disappeared because they couldn't buy anymore. There was no specific silicon industry for PV. After 10 or 15 years, now there is specific production of silicon for PV, not only for electronics and taking the waste to. There is specific production of silicon for PV industry. That is the reason why we have now new manufacturers, Q-Cell, Sun Power, and things like this. But it is funny to know the story of why it was BP and they disappeared, and because they disappeared because there was no more resource. So this is raw materials, silice, quartz. There is purification process. There is treatment. There is, I will show you, it is heating at a high temperature to melt, like the glass, okay? Then you have silicon block. You cut this silicon block in very small pieces with iron, with diamond, okay? The width of a solar cell is around 150 micron, okay? So it's very thin. And then you treat, so you dope by bore and phosphor, and then you put some, it's usually some silver, okay, to collect the electrons and to bring it outside. It is a process. So it is the main reaction that are done, but the furnace are going at 2000 degrees. Okay, so it's quite high. So when at the end of this slide you have a life cycle analysis, at one stage there was criticism about PV. Say, wow, you have to oblige to reach 2000 degrees to manufacture the PV. You have a lot of process. And, are you sure that your PV modules will produce as much as energy during his lifetime, that the energy required for manufacture? And finally, yes. Oof. The answer was yes. But in facade, when you integrate in facade, which is not very optimized by for the sun, it will be about 4 or 5 times. He will produce during his lifetime 4 or 5 times the energy that was used to manufacture it, whereas in the roof it could be 10 times. Okay. So these are the main process. Okay, you are manufacture some block and you cut some slide of this block. Okay, treat, put the the connection and have the module. I will show you real image. So this is a big block, okay, of silicon. Then you cut this big block in lingot, in block, and then you cut all this in 150 micrometers. To treat, so this is treated and then to assembly. This is a real way to assemble, because we work on a colored PV, so we work with a company. So when all the cells are ready, you connect them in series. Then you put what you call the resin, EVA, and glass to protect the cells. And then you have again to heat. Okay, you have to heat, not at 2000 degree, but around 200, 150 degree to allow the EVA to melt. Okay. But what is very important is the temperature. So the manufacturer never gives the temperature. They heat the panels in order for the resin to melt, and the time. Okay, temperature and time is very two important parameters. They are important because they are conditioning the future evolution of the PV panels. You can have the same panels when they are manufactured, it look like the same, but after in time it will age differently if these parameters are not optimized, time and temperature. You will see some bubbles that will appear after 2 years, for example. You can have delamination. I will show you some picture. The resin delaminate, whereas when they are just manufactured, you don't see nothing. Okay, so very important parameter. Here you can see some colored PV cells. It's the same PV cells that this one, but we have just changed the widthness of the anti-reflective coating. The blue color is the anti-reflection coating. Okay, like you have sometimes in your Google, you can see some blue. So it's anti-reflecting coating and optimized for the conversion wavelengths. Okay. If we just change this widthness, there is interference with wavelengths, which is different, and we'll change the color. Only changing, it's like the butterfly wing. The butterfly wing I all made in the same way. It's some particles, but changing the widthness of this particle layer on the wings of it will change the color. It's the same principle. When you see different color, it's not being painted differently. It's just the anti-reflective coating width that has changed. Very interesting. Of course, you are losing a bit of efficiency because it's not exactly the anti-reflection coating for the wavelengths of conversion. Okay, but you can have the color you want. I will show you some pink color, we have played a lot with that. So you can change the color. Here the different way of that. Just why difference between crystalline and polycrystalline. The first process to melt the silicon is the same, but if you don't control the solidification, when this cool down, okay, you will have some solidification in the materials randomly, okay, and this random solidification will give you crystals, different direction of crystals. So that means that when you will cut that, you will see the footprint of these crystals, okay, and you will see that if it is not controlled. If you are controlling the cooling by magnetic field, you will impose to have a solidification in one direction. And so when you will cut, you will have one perfect surface without different footprint like this. So you will have monocrystalline silicon, except of having polycrystalline. That explains the fact that it is more expensive because there is more control during the manufacture. Okay. One other important thing is that during this process, the cut, the loss is very important. You can imagine it's very thin, and to cut 150 micrometers is very dangerous. So you have a loss at this stage around 50%. Okay, because if one of the cells is not perfect, there's a crack, there's a break. So then it returns at this stage. Okay, it can return till you have didn't put the PN treatment and the anti-reflective coating treatment. If you have already treated, you can't do nothing with this wafer. So it is also important thing that when you reach this stage and when you are dealing with life cycle analysis, it's difficult to do something with the cells after. You can recover silver, okay? You melt the silver and you can keep it, but the wafer which is doped, PN, plus with the anti-reflective coating, you can't do nothing with it. Okay. With that you can, but okay. So classical module characteristic. Usually the tension at the born of the PV is 24, 12 volt. Okay, and you have to connect in series. So in series you had the voltage. In parallel, you have the same voltage to build the PV central that you want, okay? You can reach 88 volts, more volts at the born of the PV central. They give you temperature coefficient, so for the intensity, for the tension, but what is very interesting, it is for the power loss. That means that you will lose 0.43% per degree compared to 25. Okay, I remind you that the tests are made at 25 degrees. So it never works at 25 degrees, especially if it's integrated in a building. And during summertime, on a rooftop, you can reach 60 degrees, for example. Okay, so you have a power loss, 60 minus 25 multiplied by 0.43. So in time it could be important. That is the reason why there is focus on the operating condition of PV module. Now there is specific study on both sides of the PV module, because imagine you are in the city. In one side you have the building, so that means it is not naturally ventilated by wind, or so the temperature is higher. And in the other side you have the urban climate, which is supposed to be higher also due to heat island effect. The temperature inside cities is usually higher than outside the city. So you have in both sides of the PV module, you have extreme environment. So that's why there is also focus on the side of the urban climate. Okay, climate. Okay. Okay, so yes, the main point is that with increase of operating temperature, the efficiency is decreasing, but also the aging is increasing. We have noticed that the aging of these components they are aging faster. So the idea was to, okay, there is PV, there is thermal, we need both for buildings. PV don't like too high level of temperature, so there is a lot of research for integration and to try to cool down these PV modules. So typically with vertical facade. We have worked a lot on natural ventilation, chimney effect. So yeah, when you have an air gap at the backside of the PV panels, try to enhance the natural ventilation inside by chimney effect, and to use this ventilation for engine of ventilation in the building, for example. You can put both, so you have juxtaposed system, PV and solar thermal, and there's a lot of study of PVT, so how to recover a part of heat. So as I told you, there is 80% of solar which is coming on the PV modules which is not used and it lost in thermal. So you can play with that. The classical electrical characteristic I showed previously, already. It's the same at the scale of PV panels. So you can model the PV panels as you are modeling the PV cells. So you have a generation of intensity. You have a circulation of intensity due to the junction, Pn. You have the resistance of the PV panel, so the shunt resistance, and you have loss due to the bad manufacture of the PV panel. Every PV panels have a resistive loss in the due to the manufacturer. Okay, so the classical PV curve is very important. You have the fill factor. So the difference, the ratio between the maximum power and the open circuit and the short circuit intensity products will give you the fill factor. It's very important factor which gives you an idea of the quality of the cell. Okay? Or the PV panels is the same. If the fill factor is important, that means that the PV panels or the PV cell are not in a good quality. Okay. If the fill factor is not so bad, is not so far from 1, that means it is good. So it's a good idea also when you have PV panels to try to, because they don't give you that, for example. Or if you have also characteristic about the cells, it's interesting. So typically for monocrystalline silicon, the fill factor is around 0.83. Amorphous silicon is 0.7. Cadmium tellurium, so to give you an idea of the fill factor that you have to find for your module of your PV cells. Okay, so usually the PV modules has 12 volts, 24 volts, 48 volts. When you are in autonomous connection, you have also to have connection with battery, which has the same tension. Okay, it's very important when you have the PV central 88 volts to plug some battery in order to have also 88 volts facing this. So you are starting from the cells, the modules and the PV array. As I told you, is quite fractal. It's the same behavior. Of course, between each you are introducing some loss. So here you have some loss due to the connection between the cells, also the glass, the resin. And here, when you are introducing some loss due to the connection with cable, we will see that cable also generates some loss by Joule effect. Each time there is a loss by Joule effect. So, okay, so conventional important data are the power peak power at 25 degrees AM 1.5, open circuit voltage, short circuit intensity, and different characteristics. So usually you have this provided by the manufacturer. So the relationship between the power peak, the module surface, and the efficiency is quite simple. The power peak is equal to the surface multiplied by the efficiency multiplied by the standard radiation, so 1000 watt per square meter. Okay. So it is easy to problem. Okay. As I told you, intensity is depending of the radiation level. Voltage is depending of the temperature. The expected electrical power, okay, so is the power peak multiplied by the irradiance, okay, divided by 1000 watt per square meter. So you consider that at 25 degree, 1000 watt per square meter, the power is power peak, okay. When it is not 1000 but less than 1000, it is cross product, so it's power peak multiplied by the radiation divided by 1000. So it is what is expected from your panel at 25 degree without 1000 watt per square meter. Now, when it is not at 25 degree, you have to consider that. So it is very important that the tutorial that we will have Friday, I think, when I will speak about performance, we will see how from a real installation to identify the global efficiency. But it is a part of the demonstration. So I remind you, if you are in standard configuration, you should have this. If you are not at 1000 watt per square meter, which is very often the case, you have minoration by the real irradiation divided by 1000 at 25. And when you are not at 25 and not at 100 watt per square meter, you have to correct this electrical power. Okay, the electrical power that you have at 25 degree, you have to decrease it considering the temperature of the cell. Okay, we have seen that it was the temperature factor was minus 0.43% of loss per degree. Okay, so this is 0.43% per degree multiplied by the difference between 25 degree and the real temperature. What we are or manufacturer or integrators are making some short cut, is that they consider this temperature as the ambient temperature, which is not the case. In this formula, Tc is the cell temperature, which obviously not easy to evaluate. But it's not for sure the ambient temperature. At least it could be the PV surface temperature, which is closer. But in reality, this formula is established by the cell temperature. So when you are modelizing your PV panels, you have to integrate a node of temperature at the level of the cell in order to have a better estimation of this power. Okay, it is cell temperature and not ambient temperature, which is for solar thermal efficiency, it is ambient temperature that we consider. Okay, so I told you the main advantage of silicon crystalline is that it is quite stable, quite mature. We have a lot of experience, of feedback on it, technology and so on and so on. The main inconvenience is that it is the most dependent of the temperature. Okay, it's around 0.5, 0.45 degree per degree. Whereas, as I told you, amorphous, for example, amorphous silicon is less dependent. It's 0.2, but the efficiency is less also. Okay, so you can have different evolution of different technology depending of temperature. Okay, there is some way to approximate the cell temperature. So the approximation is the ambient temperature plus the normal operating cell temperature. Okay, so it's 25 minus 20 is multiplied by the irradiation divided by 800 watt per square meter. So it's an approximation. There is more efficient model when you are modeling. This is more for practical evaluation. Now in some code, or you can find a lot of PV module models that provide you the cell temperature depending on the outdoor condition. Okay. Okay, the wind effect has also a lot of importance. You can see that on a real PV central where there is no wind, fully sun, and a kind of very short wind period, you can see that the temperature is changing and it will change performance quite a lot. So it is the reason why, as a BIPV, if they are not ventilated or not cool at the backside, you are inducing a decrease of the performance. So the wind effect has a big effect on the performance, but it is not so well known at that stage. Okay, so small exercise now. I'll leave you some time to think about. So we have a photovoltaic modules of peak power of 250, well ventilated, with standard node temperature of 50 degrees. A temperature coefficient of minus 0.5, so it's quite high sensitivity. Submitted to a radiance of 600 watts per square meter, and an ambient temperature is 30 degrees. What is the electrical power delivered by this module? Okay, so we have seen that previously. Estimation of the module temperature or cell. We want to have the loss due to the temperature elevation and the electrical power delivered. This development, so we will see more deeply on a real installation to identify what we call the performance ratio. The performance ratio is a kind of efficiency, macroscopic efficiency of the PV central, trying to evaluate at each stage the loss. So the loss that could be to the temperature, could be related to the cable connection, in real life could be related to soiling. Okay, I saw some PV panels on the roof. There is some soil, some dust on it. It could have an effect, and so on. So I give you the answer. So the module temperature. So we can go back to the formula. Okay, is TA, the ambient temperature, so it's 30 degree, plus noct, so we said 50 degree, minus 20, minus the radiation is 600, divided by 800. Okay, so we have an evaluation, thanks to this technique, of cell temperature of 52.5 degrees. You see, the ambient temperature is 30 degrees. So it's quite different. If you make the mistake to take, okay, the ambient temperature to evaluate the power generation, there is more than 20 degrees of discrepancy. Then the power loss is related to the dependency of temperature. So you have minus 13%. Okay, so compared to the power that you will read when you will buy the module, for sure you will have never this, and you will. Here it is not a very delicate operating condition. If you have 1000 here, it will be warmer, and so on and so on. Then the electrical power which is delivered is decreased with this, and so you have 129 watt. Sorry. Okay, so it's a way to evaluate, simplify the evaluation regarding the characteristic of your modules, the evaluation of your electrical power that will be delivered. Okay. So, as I told you, more and more now we are looking also about the aging and the decrease of the performance. So these are classical decrease depending of the technology, okay, in time. So from the beginning you are losing quite strongly at the beginning, on the 25 years, for example, and then it's become more stable and more regular. But this is established in a controlled condition and in not a different operating condition. And we have identified that for specific integration condition in building, this could be huge. Okay, so as I told you, when it is not well ventilated or cooled, you have a loss of production, instantaneous loss, okay, but in time the aging is faster, and so now it's also subject to study about that. Depending of the operating temperature, mean operating temperature, are we able to evaluate the decrease of the performance in times? So this is also part of predictive model. I was speaking this morning, and also with a lot of data. These data were required in order to be more accurate, depending of the way they will operate, to evaluate the decrease of their performance in time. Okay. Now we will start. Do you have any question? Yes.
Let us say I have a situation that intensity is around 1000 watt per meter square, but my operating temperature temperature is less than 25 degrees Celsius.
So it's better.
So then what will be the efficiency? It will produce more than the power it is producing in
Yes.
the standard distillation.
Yes. When it's cooler, it's a good question. For example, in our surrounding, in the mountainous area, during winter time, we have identified that the PV central were producing 25% more than what was expected. And there is two effects, and we want to identify which is responsible for another. There is first the albedo, because there is snow, and so there is reflection. Okay, but there is also for sure temperature effect, and so we will make some measurements to see which is responsible of on this global increase of efficiency. People that it was on a big parking for car park in the alpine ski station. They said, "Oh wow, we are producing more than expected, 25% every winter." So they were very happy. And so now we will try to identify which is the effect of temperature, which is part due to albedo. But yes, when it's cooler, it's better. So it is also explained why Canada, in the north of Canada, they are integrating PV central because there is temperature and albedo, which is interesting. Other question? Yes?
So we have seen that trend in architecture that most of the high-rise buildings in India are influenced by Western designs that has glassy facades and windows. But India is much warmer compared to the European countries, with designs of big glasses and windows are now causing phenomena like artificial sun, which are causing the windows much more warmer. So my question is that how can we integrate solar PV in buildings now, because they also have glassy covers, which can create similar problems.
I agree. It's a very good question and remark. Very good. At that time, we are investigating the fact that if we integrate massively PV panels in cities, what will be the effect on the urban climate? We have not yet the answer. There is a controversy about that. One is, okay, it is glass surface, it's dark surface also, but if we look at the global budget of the city, in principle, if all the surface are recovered of PV panels, in the global energy budget of the city, you have to extract 20% of radiation, which is converted in electricity and which go in the cable, in principle. That means that compared to the same kind of inactive facade, you will extract a part of energy through the conversion electricity and go in the cable. So some things that it will have it will not induce worst consequence. Some things that yes. So at that time we have a joint PhD co-tutel with UNSW on this topic, using meteorological tools in order to model quite accurately the local climate and to see the influence of such a surface on the heat island effect or not. It's a very good question where I have not the answer. And if the answer is yes, it's induce bad thing for urban climate. It is good for innovation. We have to find selective PV panels that collect what is required and reflect to this what we call the atmospheric windows, the bad close infrared radiation. So it's it's a very good remark, but we have not the answer yet. Because if we consider that the main energy needs are in cities, we have to produce locally to use it locally. So we plan to develop a lot PV integration, but it is so a question, what will be the impact on the local climate, and the reverse, what is the impact of the local climate on the PV conversion? Because as I told you, it's very sensitive to temperature, but also radiation. Depending on the pollution, you have not the same as you shown this morning. And also the soiling, because in cities there's pollution, so soiling effect is important. Birds also, dust. So there's many issues that has to be investigated on this area, and very a big question that are interesting to answer. But we have not. If you look at the paper about that, you will find two different point of view. In my point of view, I think that it will allow to extract some heat in the energy budget of the city due to the PV conversion. Some don't agree. They said it's more dark, so they will have more convective heat exchange with urban air, so it will warm up the air and so on. So try. Yes, it's a very interesting study. Me, I for the side of PV, and the supervisor in Australia is from the side of urban climates, and we don't agree about the results. At that time, the PhD seems to find the results more in the sense of PV integration, that saying is not so bad, and the other supervisor don't agree with these results. Said that, no, it will warm, it will contribute too much to the temperature in cities. So, but we try to investigate that. Other question? So we can start on the. I don't know what time is it. I have 20 minutes to just start to try to cool down and to show you the different. So the simplest way to use solar PV is to use it when you are producing. Okay, so it is one of the lecture we will do. It is solar pumping. It was the first application developed by the petroleum company. There's a lot of book about that, solar pumping. So you connect your PV to a pump and then produce water, extract water when you need. So there are also other application, but this is with battery, for example, whereas this is without battery. Okay, it's the most simplest way to use. So to use the sun, following the sun. Okay. Then you can complexify. You can add the battery because of course there is some energy needs that you can't feel during the night. Okay, so you can have if you add a battery, it's better to add the components that is a regulator of charge and discharge. This regulator allows also to protect the battery for big peak of production. So if you add a battery, you can use it directly, but it's not really a good advice because yes, there is some fluctuation on the production. It will be not very good for the battery. So add a regulator. And with this kind of regulator, it's better to also add the MPP, so maximum power tracking. So it's electronic components that will determine, depending on the condition of radiation and the temperature, what is the maximum power. You see the curve, okay? and will identify this maximum power to fit with the PV production. Okay, so this is good to win some energy efficiency of your global system. So with a battery, minimum regulator to protect the battery, okay? And if possible, as you are adding some electronics, to have both a regulator of discharge and charge and a MPP that will evaluate the maximum power of the PV central. Okay, and then, so for here you can, whatever the need, just charge the battery, and then when you need energy, you go on the battery. The second simplest way to use. Okay. Then you can complexify. So you have the charge and discharge MPP, and you can choose to use when you need directly or to charge. Okay, to charge or to use. And also, if you use with continuous current, it's okay. But if it's alternative, you have to convert also. So to have an inverter that will each time you have a conversion, note that you are losing. Okay, you are losing when you are charging. You are losing when you are discharging. You are losing when you are converting a continuous current to an alternative. Okay, so each time you are losing part of energy. So you are complexify. So it could be good because you have flexibility of usage, but not that each time you are losing. You can have so MPP tracker and also that allow to convert continuous current in alternative current, okay, directly for the whole use. Typically, this could be applied for a grid connected, okay. Now, more and more, we found hybrid system that when you are producing electricity, you can charge the battery if the price of electricity from the grid is is high. If the price of electricity is low, of the grid is low, you are using this electricity, okay, and you are charging your battery, okay. And if the price of the grid is increasing, you are using the current coming from your battery. Okay, now, especially in Europe, where the price of electricity can have big fluctuation, some are putting in their house some battery. You can have hybrid system with. This is quite old also, combination. There were combination of electro generator with petrol, okay, electrogen group and PV. So when there was no sun, this group, when we are not connected to the grid, produce some electricity. You can charge the battery and you can use it. So this kind of system is quite old. Also, but you can combine this with one turbine, for example, instead of that. So in terms of resource, there is a combination when you are disconnected. You can have only the PV that will charge the battery that will be used for the use, or direct use of this electrogen group. So you have many ways to connect finally. It depends of the way you will use your energy. Okay, what are the needs? Are they constant? Are they during the day, during the night, so you can have many things. Now, as I told you, you can connect to the grid. And to use the grid also to charge your battery. If the price is very low, you have interest to charge your battery because you charge at a very low price. And when the grid price will increase, you stop and you use the charge that you have in your battery. I was speaking about sovereignty in Europe. This kind of principle is used at the bigger scale now. There is some attempt of storing some water in mountain, for example, for little village. So to create a kind of water loop, closed water loop, in order when the price of the grid is low, to pump the water at the higher tank, and when the price of the grid is becoming high, to use this dam to generate electricity for the village. It's a way to make money or to save money thanks to this capacity of storage. This could be used only like this, without sun, just playing with the price of the grid. When it's low, you charge. When it's high, you stop and you use it. Okay. But it is that it is this case. When the price is low, you charge, and when you are producing electricity, you use it as soon as you can for the day, for example. So you see, there are many. It's interesting to see all this configuration because it gives some idea of the flexibility. You have many ways. So there is not only one solution that I want to tell you. Even if you are connected to the grid, it's becoming interesting to add some storage, depending on the price. And there's many ways to connect and to use. You have to think about what is more efficient. Usually now the tools like Polyson, Archelios give you some advice about how to connect or what kind of components to add, depending on your needs. Okay. Whereas for grid connected, so it's quite simple. You have the photovoltaic. You have now obligation to be able to disconnect this from the grid, especially. So this is compulsory in France for the fireman. If there is a fire in your house and you have a PV central, it's dangerous to put some water with electricity. So you have obligation to have a shutdown outdoor security. Then you usually have an inverter. We will see the way. You can have one inverter for the whole PV central. You can have one inverter for a string of PV in series, or you can have one inverter per module. Now there is micro inverter, so it's interesting. It's to have an inverter per PV module. Like this, you will not induce some problem in the whole PV central if one PV has a problem. So if the inverter is for each modules, it's avoid to have a mismatch effect and things like this. Okay, an inverter, monitoring usually to say what you are producing and then injecting on the grid and what you are using in your house, and electric meters until the electric grids. Okay, so it's more simple finally to be connected to the grid than to have autonomous installation where you have to think about the connection and the use. Here, it's not really a problem. You are injecting on the grid, okay? Except if you want to put a battery, so we are coming more in this configuration, okay? Yes, the way to connect the modules. So it is in series, okay? You have to balance your installation, okay? And you have to connect the modules depending on the tension you want here, okay? Especially for autonomous central, okay? Autonomous central, depending on the battery you want to put facing this central, you will have, for example, a 48 volt, okay? So you know that at each panel you have, for example, 12 volt, okay? When you are connected in series, you had the voltage. When you had in parallel, you had the intensity, okay? So you have to have a whole installation that will provide the voltage and intensity you want, and to be balanced. So the same module per string. You will not put 2 here, 3 here. It's not balanced and it's not good. The PV central will not work very well. You have the same inclination and orientation, and the same light condition. That means if this one at 3 o'clock in the afternoon is in the shadow of a tree, you will penalize the whole production, okay? It's the same for PV modules. As all the PV cells are in series inside the PV modules, if there's a sheet of a bird on one cell, for example, it will create a big shadow on the cell, okay? And it will penalize the whole production of the panels. It looks like, oh, no, it's just a small dust, local small dust, but it will generate a decrease of the whole panel efficiency. And it's the same here. If there is one PV panel which is broken or on the shadow of a chimney or of the shadow of the surrounding buildings, it will penalize the whole production of the PV central. We call that mismatch effect. So they are not operating in the same condition. And if they are not operating in the same condition, they will be penalized. And of course, it is the panel which is operating at the lower level that will impose the lower level for everybody. Okay, it's not the higher best panels working in the best condition that will impose the best condition for the whole central. It is the reverse. It is the panels which is working the lowest that will generate a penalty for all the PV central. Very important. It's the same for soling. If there is a lot of dust, if, for example, you have just cleaning this and not this string will penalize the other. Okay, so that's why for uniform soiling effect and so on, the way to clean the PV central is very important also. Not to start and stop here and start here. So yes, mismatch effect is very important to avoid. You can have on the same house, for example, east and west, 2 PV central, but they have to be connected independently. So that means that each central have to be its own inverter, its own thing, okay? So that means that one will not penalize the other. So it's more expensive to double the materials, okay? I think for today we can stop here. If we have some question. So there is different way. as I told you, to connect. You can have one inverter. Inverter is to both track the maximum power production and then convert continuous current in alternative current to inject on the grid. Okay. For the same PV central, you can find all the configuration to have one inverter for the whole PV central, to have one inverter per string for PV panel in series, to have one inverter per PV modules. Of course, they are smaller. Micro inverter for each PV modules are smaller. What could be the advantage and inconvenience of this solution? Why there is a choice? And we can finish on this. Compare the three. We consider the same power, the same number of PV modules. What could be the advantage on one solution compared to another? ID?
The last one,
This one?
yes,
What for this last one?
because every panel is independent to each other, and damage in any one will be controlled there only, and it will not affect the others.
Yes, for this last one, each panel is managed by itself. So if, for example, this panel is not working very well, it will not penalize the other. Okay? The maximum power tracking is for him, the operating point is for him, and it will not create problem. Here, if there is a problem on one string, it will not induce problem for the other. Okay? But if this panel has a problem, it will induce a problem for the whole string. And this, if there is a problem anywhere on one panel, it will induce a decrease of efficiency for the whole installation. But there is, of course, advantage. The price. Okay? This is less expensive here than here, because there is less electronic components. Even if it is micro inverter, the wool will be more expensive than the centralized monitor management. Okay. But it's becoming very popular and very interesting for maximizing the performance of a PV central. Second is also, if this is a breakdown, the whole central can't operate anymore. If there is a breakdown here, it will not affect the other. Okay? So efficiency and avoiding to stop the production. Here is the price because it's centralized, but it is less delicate to identify where there is a problem also, because you will see that globally on the PV central there is a problem because what is arriving here is not what is expecting, but you have to identify where is the problem. Here it's more easy also. If you see that at the end the production is not so high, it's very easy to identify which one has a problem, because usually they give some information also. Okay. Okay, so we can stop here for today. If you have any question, or don't hesitate. So tomorrow we make some examples on the sizing. Thank you. Bon, c'est bon.
Thank you very much. It's a very nice presentation. I think everyone got the idea and fundamentals of PV systems. Okay? And same will be continued the next class.
Yes.
So, thank you for your patience. But I request you all, please be here by 9:30 tomorrow. And you can enjoy the campus. You can walk in the morning walk, evening walk. And then a lot of food stalls here. You can go around and you can